You can see my webcam as well, right?
Yes, we can.
Perfect. So it's right at 8. Should we start?
Yeah, please go ahead.
Good morning, good afternoon, and good evening, everyone. Thank you so much for investing your time and joining today's workshop. I'm still trying to figure out this. Okay. My name is Ravi Agarwal, and I'm a technical sourcing manager at Facebook. And I want to thank OCP and ODSA for providing this opportunity to hold first ODSA Chiplet Business Workshop. A huge thanks of our panelists, speaker, and OCP marketing team to make this happen. I want to thank our sponsor for today's workshop, both Facebook and ASE Group. And it is my immense pleasure to introduce today's workshop agenda. And we have a lineup of great speakers and panelists. They cover 22 companies representing entire chiplet value chain. And the way we have thought about the value chain for chiplet is design, build, and deliver. We will start with why chiplet marketplace, why we believe in this open ecosystem, followed by few keynote, which will be covering state-of-the-art chiplets. And then we will have 3 panel, one for each section in the design, build, and deliver. Each of the panel will have a keynote to begin with. And some of the logistic announcement I would like to do, there will be 2 coffee breaks and some poll in between to get your feedback. And Michael will help us in keeping the time so that we will be on time. And with that, I would like to invite Bapi Venokota, who's ODSA chair, and because of his vision, here we are today. Bapi.
Good morning, everyone. Can you see my screen?
Yes, Bapi. Go ahead.
Okay. So we're off to a bang-up start. We're already ahead of schedule. Ravi had 4 minutes, and we're down to, he's only taken 2. I want to welcome you all to the ODSA workshop, the Business Enablement Workshop. My name is Bapi. I am the sub-project lead for this inside the OCP, and I'm also a system architect at Broadcom. So today, this is our biggest workshop ever, bar none. So, and it's happened because of this huge effort from DJ, Ravi, Rishi, many others. We've just blown through everything we've done, and I believe we're even one of the largest OCP online workshops, or offline. Now, if I can leave you with one message after my 3 minutes here, we need you. So after the workshop, we need you to join us, participate actively, join a work stream. So as a group, the ODSA as a whole meets once a week on Fridays at 8 a.m. For the meeting happens, we're reusing that slot today for this workshop. In the next few Fridays, we're going to talk about test chips. There's a few companies that are interested in building test chips. We're going to even present a market survey on chiplets. We're going to have a discussion on chiplets from an organization in France. Have somebody come in and talk about how we want to build a POC in software, memory in chiplets, so a wide range of topics. Join us there at the very least. The activity of the ODSA happens in 3 broad work streams, excuse me, 3 broad areas. First thing, we try to define an open technical interface. And in fact, we've had a lot of workshops on this, there's a lot of documentation on this. And the second thing we try to do is build reference designs. So we built a board POC. We want to build a test chiplet for the bunch of wires data interface we're developing. But most of all today is about our third topic. And you know, the team organizing this workshop has done a fantastic job. We want to figure out how doing business with chiplets is going to be different. And that's what we're focused on today. So again, what we'd like you to do is join us in one of our work streams. We have several of them in flight. We have work streams that define the bunch of wires, a die-to-die PHY, a logical interface between chiplets. So essentially, one of the things that we focus on as a group is when you connect two chiplets together, you don't have to just connect them physically, but they have to exchange logical information. So we have groups like the bunch of wires, the OpenHBI group, the link layer group, all of which focus on the physical and logical connectivity between chiplets. We have building groups that build the POC hardware and software. In fact, we're trying to build a storage application. We'd like to have people join us on that. And we're also planning on building a test chip for the bunch of wires die-to-die interface our group has defined. We have workflow groups as a CDX group, and the thing that's kicking off this, highlighted in yellow, the business group. It meets on 9 a.m. at Fridays, immediately after this meeting, after our regular ODSA meeting. So join any one of these, join more than one of these. We could use all the help you have to offer us. So in case I haven't made it clear, join a work stream, the work streams meet weekly. We can use contributions of all sorts. In terms of our immediate needs, we're trying to build a storage application of the POC. We need help with a business work stream, active participation. There's a lot of documentation we produce, and we are also trying to grow our activities in packaging and test. So you can make a board test chip, you can make IP for the bunch of wires interface, a whole bunch of ways you can participate. There's a lot of information on our wiki. We have our recordings from our weekly meetings, a bunch of presentations and previous workshops, all sorts of stuff. Join us there. I'm not going to cover them, but in the deck that we'll upload, I've left a lot of reference information. One is the kind of activities we have done as a group over the last few quarters, and the last is we're extraordinarily rich in what we publish. So there's a whole bunch of pointers to papers by active participants in the ODSA. So with that, with a couple of minutes on the clock, I want to thank you again for your time. Thank DJ and Ravi, DJ Ravi and Rishi and everybody else for putting together this bang up workshop. Thank Michael, Archana, Dirk, and everybody else at OCP for getting us to where we are. Thank you. Enjoy the day. I'm done.
I think the next we will go into state-of-the-art chiplets section. So we have our first speaker.
Okay, hi everyone. This is Javi Delacruz with ARM, and I'm going to cover the need for establishing a chiplet ecosystem. But please note that the opinions expressed are my own, really, and not necessarily those of ARM. Go ahead and share my video as well. Next slide. So I think in discussing this, one thing that's really important is to note what is a chiplet. So what's key to note and how it differs from a die is really the interface. Chiplets are really optimized for die-to-die interaction with package. They really should lack the drive strength to be able to be packaged independently. And by using die that are optimized in this manner, you're going to have an overall more efficient system. So there are a few barriers and drivers to these. So let's cover the drivers first. And really, there are three drivers, and any other driver you can think of somewhat ties into one of these, and these are all interrelated with one another. So the reticle limit is something that's been talked about regularly. AMD has brought this up several times over the past few years. Given that silicon is not scaling the way it used to, we're bumping up against these reticle limits for some applications. So needing to split silicon into various pieces is becoming a need there. Similarly, it's also been discussed more recently and is becoming magnified by the increasing costs on a per wafer basis in emerging nodes. You have the potential of saving a lot of money by partitioning die into smaller die, testing them individually, and reassembling them. In emerging nodes, the die by far is the biggest cost driver, and improving the yield of these die can have a significant impact on the overall system cost. And lastly, and what is the charter of ODSA is heterogeneity, particularly heterogeneity from different sources. And there's a few barriers to that which we should discuss. Now, before we go into that, the first two I mentioned, reticle limits and cost savings, are problems that vertically integrated companies are going to face, but they are able to better manage them. For the companies that are less vertically integrated, heterogeneity will be a bigger driver. So as far as drivers to that go, taping out each of these die is not a small undertaking. It's quite expensive. So we need to have more of a community be able to share in these costs and deliver these devices to the market. So starting from scratch and taping these all out yourself, is not practical. It just may not make any sense. And in order to have these devices made by different companies, it's important to note that we need to make sure that they can communicate with each other effectively. Again, these need to be common standards, ideally optimized for die-to-die communication, not just taking a die that's already packaged elsewhere and just putting it into a package, because that's really just an MCM at that point. Just note, there's different things that drive this die-to-die interconnect. Some of them can be ones that are well positioned for conventional laminate packaging. Others will drive up the cost and going to a 2.5D-like solution, needing an interposer or something similar. So whichever one is the most constrained will drive the overall cost of the system. So what's important to note is how does a user identify where these die are, what their capabilities are, and also get the necessary documentation for them? How is it tested? What kind of power will this dissipate? How well is it tested into, what yield coverage? Because that'll affect the overall system cost later. There's lots of factors in here that need to be accounted for, and the user base needs to have an easy system in which to identify all of these. And lastly, the gorilla in the room is going to be who's going to own and enable the inventory to ensure that inventory is available and own that yield. So that's something that needs to be addressed. So it takes a village. What's going to be important here is as you design a new device, and this is my ask of the audience, please keep in mind the need for reusability. For example, if you look at the upper right, you can see an application. You have several CPUs to an I/O hub, which is an emerging use trend. And if this CPU could be designed with a non-proprietary standard, but a more open standard, it could be reused in applications such as this idealized Mara chiplet design seen on the bottom, which is a document referenced regularly by ODSA. So not all of these elements need to be in advanced nodes. Sometimes legacy nodes just will work better, will be more cost effective, etc. But keep in mind that one of these die will likely need to be custom or an FPGA, just to tie everything together. Having fewer interface standards to work with will make this a lot easier. IP providers that normally may provide IP for the space may not be they won't be capable of really designing and developing and delivering silicon, so they may need to work with partners. And this creates an interesting need state in the market that someone may be able to fill in. So there's an opportunity there for a new entrant into the market. And the chiplets that are needed, some of them are obvious. Voltage regulation is a significant need. CPUs, different types of array, whether volatile or non-volatile, are all of interest, will have a market. And we just need to be able to find a way to make all of these different types of chiplets and die available for the overall market so that we can really enable this vision that the ODSA has put together. Thank you.
Thank you, Javier. Now we are moving on to our next speaker, Arvind from IBM.
Hello, this is Arvind. Let me turn my webcam on and okay. Okay, so I will be talking about the chiplet business challenges for AI accelerators from IBM Research. So IBM Research has been developing an AI core which is optimized for deep neural network processing, both for training applications and for inference applications. We recently published the 3rd generation of our AI core, and a lot of the driving motivation for the development of these different cores, which has come in stages, has been the scaling of precision. So we have tried new algorithms, which has generated new hardware and new parts of the core, as you can see from the plot on the right. And with an AI core, we recognize that there are many diverse use cases that can require different numbers of cores, different functionality in the cores, different memory requirements, and certainly different power envelope requirements. But it's really not possible to tape out a new SoC for each of these new applications. So for us, one of the big value propositions of a chiplet-based ecosystem is this ability and flexibility to create right-sized and modular solutions, which would integrate diversity in the AI compute, the I/O and the networking, and the memory chiplets. So to illustrate this a little bit further, here are some of the different use cases which have very different requirements, which can range from the IoT and sensor all the way up through mobile, automotive, and data center. These have different core count requirements and very different power envelopes. From a workload point of view, the IoT sensor through the automotive will typically require mainly inference. And at the data center level, we can see both training and inference. From the point of view of core counts, the number of core counts is relatively small on the left, and then it grows as you go to the right. So certainly for the first 2 or 3 of these application spaces, from the IoT sensor up to automotive, we could envision having smaller building blocks that could be used to create larger units. At the data center level, we are looking for high core count densities and compute densities, which can get even large for training, where we were talking about multi-chip systems to do large training jobs. And so the requirements might be quite different. The technology requirements can also be different in the sense that certainly the IoT sensor, mobile and automotive markets would need lower power, and that could be also for cost reasons desirable to do in an older node, while data centers will likely use high performance technologies and leading nodes. The power envelope requirements are also clearly different between low power for the IoT sensor up to the automotive markets and a higher power envelope for the data center requirements. For many of the IoT and mobile requirements, latency is very critical, whereas for the data center, latency may be important, especially for small mini batch types of applications, but throughput also becomes key. And in terms of packaging, low cost and low form factor, small form factor are very desirable for the IoT up to the automotive. While in the data center, we have focused on advanced packaging to support the much higher bandwidth requirements. And so again, we view chiplets as a way to achieve composability and scalability for solutions across a wide spectrum of these use cases. That involves networks, precision, the low precision that we talked about before, memory requirements, and different power requirements. So how do we view these chiplet business challenges? On the right, I've shown a cartoon of what we view as kind of an idealized platform with a high compute density and a lot of flexibility in the components which are connected by these high bandwidth and low power interfaces, and may involve a variety of components, including some specialized components. And I've grouped these into 3 different types of challenges per the theme of today's workshop. In the design challenges, those would be really for prototyping and design tools. And this recognizes that end user applications are constantly evolving. So there are new AI workloads coming up all the time. There are new networks that are being introduced, and these new workloads often have different compute and memory balance requirements. There's a need for rapid research prototyping of new AI cores. So a chiplet ecosystem could provide us with a platform which allows us, for example, to rapidly develop and prototype cores to address these needs while reusing other components such as the nest. A third area really comes in EDA, where because we're now talking about an entirely different platform with chiplets, there need to be a co-design with chiplet and package and PCB. One of the things we've encountered, which would be desirable to address, is the standardization of input and output formats across different tools, and a full tool suite to support the implementation verification flows for chiplets rather than for chips. And that includes complex chip package interactions, thermal, and other aspects. From a build challenges point of view, I think just going back to the last talk, we'd like to see a kind of a chiplet marketplace, which would offer support for a broad variety of IP in the chiplet format. That would include things like memory, I/O, and accelerators, as well as open standards for these I/O interfaces. We view the interfaces as going hand in hand with packaging in terms of there may need to be a variety of options that can help to meet the latency, bandwidth, power, and thermal requirements for these different use cases. And then in terms of the delivery challenges, we really would like to have a lot of multi-vendor flexibility in the supply chain, which would allow for interoperability of silicon, package, assembly, test companies, and methods to enable various chiplet and packaging options, much as the way, for example, in an automobile situation where you can just interchange the same battery for your car, you have a variety of options. You aren't necessarily tied down to one particular option. So those are how we view the chiplet business challenges. Thank you.
Thank you, Arvind. Now we will move on to our next speaker. Do we have Bill from Bill Chen?
I'm right here. I'm looking for the how to share.
We can see your screen, Bill.
Do you see my screen?
It says go to webinar. It doesn't show the presentation.
I don't see it yet. So do you see my screen?
Yes, we can see your presentation now.
Okay, excellent. So good morning. My name is Bill Chen. I'm going to speak today on the heterogeneous integration roadmap, which is very much consistent with the advancements and implementation of chiplets. I want to acknowledge the contribution of the Heterogeneous Integration Roadmap Technical Working Group. So we have 22 chapters in the roadmap. We start with systems and market applications, high performance computing, mobile, medical, automotive, IoT, and aerospace defense. Then we have chapters on co-design and simulation, integration processes, SIP, wafer level packaging, 3D and 2D. We have the building blocks and then cross-cutting topics. All together, 22 chapters and available for download for free from the IEEE website. We had recently had a 4th annual meeting where we have a symposium and with plenary speakers, and day 2 and day 3, the technical working group presentations. I will be showing you some of the slides from the symposium and also the technical working groups. First of all, the presentation from DARPA, Dr. Gordon Keeler, and he showed that we are in the 4th wave of the electronics in the electronics Moore's law era, and we are on the fourth wave, which is heterogeneous integration. He showed the drivers in those fourth wave, and then he also showed areas which is bringing in the DARPA photonics program. All of that is available for video viewing at the link that I had just showed. So first of all, I want to show a slide from the HPC data centers, and what you see in red is what is on the 2019 roadmap. What you see in green is going to be implemented, added to for the 2020 update. Also show a slide on wafer level packaging. This one is from on John Hunt, and once again, what you see on the left is the 2D and 3D fan-out packaging. On the right is a hybrid packaging. Particularly, you can see some of the new innovations that is implemented. So what that says is that there's different alternatives in advanced packaging for the implementation of chiplets. Also, this is a page from the test technical working group, Dave Armstrong and Ken Linear, and you can see the different sections in that test chapter. And as shown in the bottom over there is a output from a team of 120 test experts, and it's very much important for the chiplets community with these with the chapters available and resources available. And what I want to show here is the 2019 roadmap chapter. It was launched in it was launched on October 10th, 2019, and 24 chapters and 590 pages. And just look at the press release. What it shows is the objective of this roadmap. This is for the future of the electronic technology and potential solutions. And it is to stimulate pre-competitive collaboration, just what we see over here today from the discussions of chiplets, sponsored by the 3 IEEE societies and ASME as well as SEMI. And wrapping up, since the release of the roadmap, the roadmap has made its mark in the global electronic system, and our journey is off a very strong start. ODSA and the Heterogeneous Integration Roadmap share a common objective to foster the chiplet implementation and also the business implementation. Packaging technology for heterogeneous integration serves a link for the design, build, deliver collaboration before the wafer foundry and system integrators. And AL and ML address the stakeholders' collaboration data sharing. This will mitigate the risk across the whole supply chain. Finally, I want to thank you and acknowledge the roadmap technical working group contributions, and the download link is what we have shown over here. I have shown my email address over here, and I would invite all of you to contact me for any of the information that you might want to see. So thank you very much.
Thank you, Bill. Now we'll move on to our next speaker, Gri from NVIDIA.
Can you guys see my screen?
Yes, Gri, we can see.
Thank you. Thanks for inviting and listening. I'm relatively new to the ODSA. I have been attending the last 2-3 sessions. Let me put in the presentation mode. So there is the perfect storm of three things that essentially pushing us towards adopting these chiplet standards. These three things are exponential growth of computational requirements, essentially largely driven by the recent growth of the ML, DL, and AI advances. The second thing is the application and algorithmic diversity that's growing, requiring heterogeneous adaptivity to these algorithms. And the third thing is loss of general purpose processor performance improvement, largely due to diminishing process technology benefits, and in the most recent cases, increase of price of per transistor costs starting 20 nanometer or also. So the only way to solve this is to have architectural innovations to keep pace, to offset the loss of performance growth due to process technology. And this requires this heterogeneous design of functional blocks, and potentially these blocks are ideal for splitting into chiplets. So that's kind of the rationale for driving towards chiplets. So everybody knows here the design flow. Just to level set, typically a design cycle from scratch takes approximately 4 years. Yet once you start, there is a pressure to deliver approximately every 18 months a new chip or a new spin. This requires at least 1.5x the team size to execute this flow. And the wafer costs, EDA tool costs continue to grow with process technology improvements. And this is rightfully due to growing complexities, whether it's multiple masks or the design complexities of dealing with this fine process technologies. As a rule of thumb, this is not a science, but as a rule of thumb, if a product doesn't sell on the order of 150K volume of chips at approximately 50% margin, you're probably not even breaking even, irrespective of the complexity of the chip, size of the chip, or the market of the chip. This is actually my experience from my previous jobs, rather than, let's say, NVIDIA specific. In addition, the companies have to make more than one chip. You have to have an ecosystem of making multiple chips if you sustain and able to continue this keep investing for the future chip generations. So the bottom line is that there is very little slack in silicon business. Proof is that almost all the companies that are existing are having trouble one time or other. Intel, AMD, NVIDIA, including everyone. So if somehow we think that chiplets will reduce the slack in the existing silicon design flow, I think that's a wrong thinking. Chiplets need to improve all these aspects of the design flow. So the two use cases are mainly that other speakers before me talked about, to overcome the reticle limit. This use case typically is performance sensitive, since you are breaking up a single what would be a monolithic die to multiple chiplets. This breakdown could be functional split of the blocks, or it could be perf split. 4 of the chiplets or 8 of the chiplets together give you the needed performance. This is less cost sensitive, but probably require parallel D2D interface and custom silicon interposer, so much more complex. The other one is coming from large to small, so bringing a board or a system into a package. This is a lot more cost sensitive, probably doesn't need a silicon interposer and special custom packaging, probably sufficient to do serial die-to-die, and this is highly cost sensitive. So irrespective of either of the use cases, there are two considerations the companies need to count for. What's the rationale for moving, if you are not reticle bound, all your chiplet, all your silicon development to chiplets, even within the company, not necessarily a broader ecosystem outside the company, and then do the necessary investment to in improving EDA tools, the changes needed in architecture, design space exploration, consisting of chiplets. Then comes the actually playing in the broader ecosystem of having to rely on third-party chiplets. So the first step is actually within the company itself moving to chiplets, and then relying on third-party chiplets. So what I call, there is some chiplet tax. As soon as you break down a monolithic die into chiplets, there is some increase in design complexity. There is loss of useful area. So there is a useful area versus perimeter area lost due to die-to-die. This could be one side, two sides, or all four sides. Increase in power and latency due to what used to be a on-die data movement moving to off-die. The built-in redundancy requirements to ameliorate the known good die problems, and then obviously increased packaging costs. So this chiplet tax can be some upfront NRE and some per chiplet tax in the form of per chiplet cost increases potentially to deliver the same functions, same performance. The government initiatives like from DARPA and others, and the industry efforts like the consortium's efforts like HAR definitely helps to at least build the ecosystem so that the more cost-sensitive companies can start playing. So the other issue is this whole standards versus innovation. Premature standardization can kill innovation. They're almost antithetical to each other, especially if the right boundaries and interfaces are not chosen correctly. It can stymie the innovation. And secondly, the standards cannot be the least common denominator of all the participating players to come up to a standard. Then it's actually driving things down. Of course, on the other hand, if without a standard, if it drags on too long, then it can become too many standards. The recent example of that being try to go post PCIe standard or PCIe standard enhancements, and the explosion of standards, C6, Gen Z, OpenCAPI, and few others actually. And then finally, some looks like a convergence on CXL. So what lessons should we learn from this in for example, die-to-die protocols and interfaces and other software and hardware standards necessary for chiplets? Some of the software ecosystems one need to think about is, especially for chiplet management and monitoring software, software for chiplet debug, the standards as well as software ecosystems, and then security. I see already some like industry leaders in this space, Intel and others are already thinking along these lines. So the other thing is for defining the mechanical thermal power delivery constraints across chiplets, is there need a architectural definition standard for the chiplets? So some of the challenges the other speakers are already talked about, the very well understood or known good die problems. Then some of the other things that come to mind is who owns the lifetime guarantees of these chips. Some of them need to work for 10 plus years in the field. When there is an issue in the field, who will do the debug? So at least initially, maybe some end users may have to share, the large scale end users like CSPs may have to share some of this risk. Then when you have such a tight schedule and a design flow, the risk of relying on a third-party chiplet to be able to deliver your product is scary, unless there is, as other speakers pointed out, multiple choices. And this comes to this chicken and egg problem that we have to solve. Hello?
Thank you, Giri.
Yep.
So I think we have some time. Dharmesh, do you want to ask some of the questions for the panelists?
Absolutely. So pretty engaging morning, and our audience is pretty active. They have a whole bunch of questions for everyone. So Giri, a quick question for you. When hitting reticle limits, it's more obvious to move to chiplets. For everyone else who are well within the reticle limits, how would you go about looking at going for chiplets versus non-chiplets?
Yeah, so that's the thing, right? So I'm not sure if my slides are still being shown. Some things are that when there is the nice thing about chiplets is potentially it can do separation of concerns. So sometimes there is high complexity, low performance requirement block along with the high performance requirement blocks. I remember in one case, just for doing PCIe enumeration, not following the standard, we had to retape out a whole 650 millimeter square chip at the late advanced process technology. So there are absolutely benefits in this functional split. And in other cases, these highly complex, low performance chips can be used across multiple generations, recouping some of the cost that goes into it. So extracting the design timeline, minimizing design timeline, reducing risk, all these things are critical to when we evaluate a chip that is still under the reticle size and like to go to chiplets.
Got it. Awesome. Thank you, Giri. So the next question is perhaps Rishi, you can answer. Power. The question is around power distribution. Let me get to the question itself. Just give me a second. One second. How can the power distribution be generalized if there's a lot of flexibility and heterogeneity? So I guess the question which Rajiv Parmar is asking is, do you see any ways to have a common power distribution schemes while there are so many differences in the designs?
Yeah, definitely that can be done by having the LDOs and the voltage regulators on the chiplet, and you architect it in such a way that you know the base layers of the power supplies requirement on the parent die, and then this particular chiplet design will be more specific for the power distribution. The LDOs and the voltage regulators are on the chiplet, and the way the chiplet integrates to the parent die, that it proliferates through the different power layers based on the voltage requirements. So in that case, you get the flexibility to program within the chiplet, and this chiplet can be used in multiple, I would say, ASICs or SoCs being designed by that organization.
Awesome. Thank you, Rishi. Next question is for Arvind. Great presentation, Arvind. How do you think our industry is doing on the general concept of common design flows and tools? I think you talked about design challenges, and one of your bullets referred to EDA tools and having commonality. So can you comment on that, how industry is moving there?
I think there has been a lot of progress and recognition of the role of chiplets and the heterogeneous integration and the many advances in the packaging techniques that have come about in the last few years. But nonetheless, there are sort of kinks in the system, especially in terms of this interoperability. Maybe sometimes when you want to use tools from one vendor, which might be optimized for one part of the flow, and a tool from a different vendor, there is a sort of a border guard. And some translation has to take place. It would really be desirable to have this be seamless. So if there were some standards or some better guidelines on how to do this translation, that would, I think that would facilitate a lot of the flows. And, as I said, I think we have to move much more towards a chiplet view of the entire process and the entire flow.
Awesome. It's a great point because we have design houses on this workshop. So I hope everybody's hearing this, your request, and hopefully we'll start working on it. There's one more question for you. You mentioned and you showed business division between, all the way from IoT to data centers, low power, low core counts to high power, high core counts. So do you expect heterogeneous integration to kind of apply across all of these verticals in a similar fashion, or do you expect that one vertical will lead versus the other vertical?
Well, I think there's certainly some overlap between these various verticals, and I tried to bring that a little bit because the IoT space and the sensor space will begin to overlap with the mobile space. Probably if there's I wouldn't say a wall, but probably the biggest divider in that vertical set of stacks is with the data center requirements. So I think there we may be looking at a variety of HI solutions, and as I kind of tried to emphasize, I think compact form factor and low power would be the ones needed for the left of that chart, and the higher bandwidth requirements and would be for the right half. But it doesn't mean that the right half, we are still also very concerned with getting to metrics like low picojoule per bit. That's also key. So I think there are different solutions for across that spectrum, but I can certainly see room for overlap as well.
Awesome. Thank you, Arvind. So thank you all the speakers. Now we are entering the design section. As we heard in the introduction, the value chain is working on design, build, and deliver to the end users. So with that, we'll have Douglas from JPL, who will come and talk to us about how they look at design for chiplets in space. Welcome, Douglas.
Hello. You guys see my screen there?
Yes.
Thank you for allowing me to attend. And this will be a little bit different than the normal conversation, but we'll hopefully you'll find some of this interesting. So the title is Chiplets in Space. And we have a picture there of Europa and Callisto circling Jupiter. So this is much older technology, but we'll try to provide a background. Where does space fit into packaging technology? So there's still a lot of ceramic parts, obviously made before many of the people on this call were even born. And then you can see the transition from the ceramic parts through the 90s and the 2000s into the 2010s of the various non-hermetic packages, which really aren't designed for space, but certainly have been used. And we do what we call upscreening, which requires a lot-specific qualification activity. And then as things have begun to move in, over the past 6 or 7 years into more commercial applications of 2.5D, 3D, TSV fan-out technology. So the swap revolution that these technologies actually and clearly enable are becoming certainly of interest to the space community, but the difficulty of how to upscreen something this complicated with the not being involved with the manufacturer at a detailed level is one of the significant problems. So always very interested to hear about the IEEE HIR.
Sorry to interrupt. We're getting a couple of requests from the audience for you to swap your display settings to go to full screen mode. Some folks are having trouble seeing the text.
That better? I had it in full display mode here.
If you check your display settings up there at the top, I think that may help. Perfect, thank you.
Sorry. Do I need to repeat that slide or there enough there? I'll probably move on given the amount of time. So we're very interested from the space point of view in the heterogeneous integration roadmap. And as discussed,
Doug, I think your GoToWebinar window is on top of your slide.
You just slide that over, Doug. Thank you.
sorry.
Perfect.
Better?
Yep. Thank you.
Okay. As mentioned, the aerospace and defense part of it drives the market for the heterogeneous roadmap, with this emphasis on the real great success that the DARPA chip programs have had, something we certainly keep track of, but the specific address issue of reliability, these are very performance-based solutions, and reliability remains the #1 space concern, because we're trying to leverage all the various other parts of the space roadmap that are being discussed here today, from the technical areas and the integration layers and all the different, from the photonics to the integrated areas to the different markets, is what I wanted, is that all that overlays, in at least in a general sense, for space. So right now, there we go. So right now, the current space roadmap is significantly different than the roadmaps we're talking about now. It's still a transition from this very classical ceramic part through resolving risk-averse concerns about hermeticity and substrate characterization, to moving into an organic substrate, and then now significant effort in a system and package activity. There are a couple of large standards bodies that are updating the MilPrep 38535, and there's a new standard, the MilPrep ATM, which is the advanced technology, specifically to try and to address how to infuse and then how to qualify heterogeneous technologies for space, including system and package. So the #1 problem that people always ask about really is radiation, and the solutions are somewhat complex, obviously, to involving in space. And so I wanted to give the heterogeneous concept is specifically important for space. And right now, the space solution, so here's a couple of things from the recent literature, is at a board level and it's not at a chiplet level, is that the solution to making radiation hardened die really begins to break down at advanced technology nodes. There's never going to be a 7-nanometer rad-hard chip. It's too expensive, and there's 40 of us that need it. You can't amateurize the cost of the amount of effort that you have to put into making these very state-of-the-art devices. So and you don't need a rad-hard 7 billion transistor device either. What you'd like to have is the radiation. So radiation is to manage and control the device, and then we have to manage the upsets on the high-performance device. And so the way to do that is a heterogeneous approach. And so, like I said, right now there are heterogeneous approaches at the board level. This one here on the left is trying to take advantage of GPU capability, but there is the FPGA that you see there is a radiation-hardened FPGA. So that's the most prevalent solution, but that's the one that would lend itself initially probably to a chiplet approach. And then the one on the right is work that I've done recently is for Europa. I wanted to show that picture early on. The radiation environments in Europa are the most challenging in the entire solar system. You can see Europa was right next to Jupiter, and it has well over 500 rad 5 gray per day lethal radiation dose at the surface. And so the mission to Juno that took the picture have the devices have to be themselves capable of 300 K-rad inside a 500-pound titanium aluminum shield. So we've advanced some more discrete technology with more advanced substrate technology to develop a series of cryogenic low power avionics for the use of Jupiter and Europa missions. But that's the more realistic landscape of chiplets as an enabler, but heterogeneous integration as the real technology platform. And then the goal and the strategic issue is how to integrate radiation hardened devices with high performance devices. So wrapping up, obviously space is still catching up to with advanced packaging technologies. NASA ranks the missions from the most risk sensitive to the least risk sensitive. So that provides a path for infusing the higher, more risky, if you will, risk averse missions to allow demonstrations of packaging and more relevant modern technology. And the heterogeneous technologies, I think, have the viable solution to this mixture that we've talked about of high performance with the radiation. And as I've shown, the PCB technologies are where we'll start, and that this die level and solutions remain very high in cost, and they certainly favor a more volume solution. And so with that, thank you very much.
Thank you, Doug.
Okay.
Now we'll move into our first panel, and Alan will moderate.
Hi, everybody. Yeah, well, our first presenter is Manuel from Synopsys. So Manuel, take it away.
Hey, Alan. I hope you can hear me well. So let me start. So what we're talking about here is, you know, the chiplet market from a point of view of the design, from a design perspective. Chiplets, of course, are not new. They have been, you know, they've been in the market for a while, but they have been a reserve for large companies that can.
Sorry,
that can develop.
Can everybody see the screen? Because I can't.
Yes,
so,
you can see the screen.
Okay, great. Sorry, carry on, Manuel. Apologies.
No problem. So yeah, so these have been the reserve for large companies that can develop their own proprietary solutions. And our goal with this discussion, within OCP, is to bring this chiplet concept to the masses, let's say, and to enable an ecosystem where smaller companies can also develop chiplets and in a way that is efficient and can address the open market needs. So in order to achieve this, there are some barriers that need to be overcome, and that's what we are discussing here. Things like how to ensure that my chiplet interoperates with your chiplet. How do I design? How do I do system design? How do I do integration of chiplets that come from different vendors in an efficient way? These are the main areas, the main challenges that we are seeing, and that we at Synopsys are focusing on. So let's go a bit over them. I think first thing is obvious. We need a common language to cover these aspects. We need a common language in terms of the die-to-die interfaces. So we need standardization. But it's a standardization that needs to acknowledge that there are different use cases with different key care abouts. Previous speakers have talked about them. It could be energy efficiency, could be bandwidth, could be cost, etc. So one size will not fit all. One size will not be meeting all the requirements of all different use cases of all different sizes of the market. So different options will continue to coexist. We are talking about parallel and serial interfaces. We're talking about different advanced packaging technologies in 2D, 2.5D, 3D, etc. All of these will continue, in our view, to coexist in the market, and we need to be conscious of that. However, still, standardization of the PHY and the interface is important. But it's beyond the PHY. It's also, when you talk about an interface, you're talking about a solution that goes from end to end, from NOC to NOC. So we focus a lot about the PHY, but standardization needs to go beyond that. And obviously, it needs to consider also aspects like interoperability. How do you validate, interoperation between two dies from different vendors that are enclosed if the connection is enclosed within the package, as well as security. I think we also need a unified design environment, again, a unified language between the different parts that are involved in the design of an SIP, be it the design level, the die level, the package level, the integration between them. So the ability to do quick system integration trials to assess signal integrity, power integrity, thermal effects during SIP design, to do multiple iterations very quickly and very effectively and efficiently is obviously of great importance to enable this this design strategy. And this is important for the integrator, because he must be able to quickly turn around in these what if examples, these what if exercises, in terms of floor planning optimization, in terms of validating, again, signal integrity, power integrity, thermals, etc. But it's also important for us as an enterprise or for any IP vendor that is involved in this market, because we also need to create IPs that are let's say package aware, that understand that that the environment where they are to be used, and so we also need on our side to do our own trials, our own mock designs, and so that we expand the validation of the the validation of the IP beyond the simplified towards including the package level considerations and effects, let's say. So again, a unified environment, a common language is the best way to expedite the turnaround time for the system design and allow a better optimization, and also reduce the cost barrier for design houses that are interested in participating. And finally, I believe we also need a standardized test infrastructure. So we talk a lot about known good dies and the need to have testability within the chiplet, within the chiplet die itself, to with high coverage, so that you can identify known good dies and only use those for assembly. But the chiplet is also a part of the SIP, of the broader system, and that itself needs to be tested after assembly. So all this testability functionality that exists within the chiplet, or within the multiple chiplets that are in the system, it must be tightly integrated in a hierarchical fashion way, that in order between the different chiplets in the system to allow efficient test within the die, within intra die, but also after assembly across the multiple dies that are that make up the SIP for a complete coverage. So I believe we need standards also for this hierarchical test infrastructure, and there are examples of these standards being developed within, for example, within IEEE. And finally, there is another challenge that we see as an IP or a chiplet designer, which is also like a limitation
if I go a little bit, we're running a bit low on time here.
Okay, I'm almost done. And this is access to advanced packaging. Costs are are prohibitive for some technologies, so they stay the realm of high volume products. Others are other technology, other advanced technologies like fan-outs are bringing down costs. So this is good. This is a good way to enable other applications and other players in the market. However, even things like access to the, let's call it, the package design kit for prototyping or design validation, these are still challenges and hurdles for smaller companies, smaller design houses that limit their access, and as an industry, we should try to eliminate them. And that's my point of view here. Thank you. Thank you.
Now Rishi, would you like to go ahead?
Good morning, everybody. And first of all, thank you for the OCP community and ODSA forum to give Cadence and me an opportunity to present and provide our insights about business consideration for chiplet-based compute products. Next slide, please. So I've tried to make it as simple as possible and get to the main crust of this discussion. Is when we are basically designing or considering chiplets, there are various criteria which one comes into play, especially for the SoC, and it's all primarily dependent upon what is your achieved target goal, what you want to do. So first one is basically we are leveraging our SOC design investments, where you have multiple SOCs within an organization. If somebody is doing a NIC card, somebody is doing a compute CPU, somebody is doing an acceleration, and within the organization, you want to basically optimize the overall BOM cost. You basically look into the concept of silicon in package, where there will be multiple dies. This also reduces the overall BOM cost from a system point of view, where individual components are sitting around us on the motherboard, and now these different functions are getting integrated inside. Another aspect of it is to optimize your investment. I would say Giri mentioned about it, where you need to do a trade-off or a selection between the node and the SOC application. By this, I mean to say that not everything on your SOC design needs to be on the emerging or the advanced process nodes. Some of the functions can be in a node which is one notch lower than the bleeding edge. I can give you an example, like if you're designing a CPU class of a SOC or a compute SOC, you would like the processing elements to be on the advanced nodes for a simple reason that you can stack much more or multiple cores on it with a lower power and better performance, whereas your IO peripherals associated with the CPU can be on a notch which is one notch lower than the emerging node. So standard interfaces like PCIe, USB, Ethernet can be on a technology node, which is, for example, in 7 nanometer, whereas your processor can be on the 5 nanometer. So that kind of a trade-off in terms of optimizing your investments can be leveraged. And secondly, when you do the partition of the design, now you're partitioning the design not on the monolithic side of things, but on a multi-die class of things. For this to enable and to accelerate the market adoption of this particular concept, standardization is a very key aspect of this. I think so many of my past presenters have emphasized on this. So when we talk about standardization, it goes from the electrical, from the functionality and the features aspect of it. And the reason why we say these three buckets, because this accelerates your testability, your yield, your predictability aspect of it. If you look at the predictability, for predictability, we need a standardized design flow. And I think so the presentation from IBM spoke about it, where Arvind mentioned about design flow. The design flow basically gets you to the predictable aspect that what you're designing and what you're going to see in actual silicon, they're going to be similar in their field functions and their features. For design flow, if you zoom inside the design flow, we have to consider methodology, testability, and integration. And when I talk about integration, it goes into thermal, packaging, all those are aspects of integration where you can meet the economies of demand, you can get a yield which is basically meeting your design requirements. So in order to get the design flow, there is not only a collaboration needed by the likes of Cadence and Synopsys or other EDA companies or tool vendors, but also a great collaboration is needed from the foundry partners. Ultimately, the tool companies are relying on the foundry partners so that there is a closer collaboration on the physical design or the physical stuff which we're going to get in our hand and the virtual world where we are living pre-silicon when we are designing it. From a foundry partner, this collaboration is necessary to achieve the right level of yields because that is the accuracy of the tool, and the tool has only that much it can do, which is common science to it. But beyond that, there are the libraries, the rules which come from the foundry partners, and also there's some aspect of standardization involved in it. But predominantly, I would say majority of the contribution is coming by the foundry partners and the intelligence being put in the tool. That basically takes care of the integration part of it and the yield part of it. Last but not the least is the leverage of this particular concept of chiplet is basically you don't partition your design the way we do it today. We do a particular SoC, we partition it as this is a CPU, this is the DMA, this is the layer 1, layer 2, which does the PHY and the MAC PCS aspect of it, or we basically integrate into an accelerator, DMA or CPU. Now basically we go beyond that scope. We are basically doing partitioning on the silicon die by itself, basically silicon in package where there are multiple dies. Now we can leverage a step beyond by active interposers, by doing NOC and doing a mesh on the connectivity of the chiplet by itself. That's basically taking this chiplet based design to the next generation where we talk about modular designs on silicon by itself, by die itself. But for all that to enable, to all that to happen, we need to basically look at the standardization, predictability, and the yield and integration aspect of it, so that we can hit the sweet spots for doing a business which is lucrative for us and for our customers. Also, the last point I would like to emphasize is the graph what I have over here. If you look at the design, IC design, and the cost associated with it, there is a significant design cost apart from the yield cost associated with it. This design cost can get fragmented by the concept of chiplets, because once you design this common chiplet, it can proliferate through different designs within the organization. You can have a standardized layer 1, layer 2 on a chiplet, or there was a question on the power supply and regulators on a chiplet, and that standard chiplet can go across your different product lines. So we are kind of amortizing the design cost aspect of it by using this chiplet. That's all I had, guys. If there are any follow-on questions, I'll be more than happy to take it.
Thanks, Rishi. And now to Tony.
Hi, everyone. I'm Tony Pialis, President and CEO of AlphaWave. We're a leader in the high-speed connectivity silicon IP space. I'm here to talk about serial or parallel. I speak to a lot of semiconductor companies each and every day. There's a tremendous amount of interest in D2D. There's a tremendous amount of uncertainty as to if a D2D is used for a chiplet-based silicon and package product, what type of interface should be used? Should it be serial? Is it parallel? And if it is serial or parallel, which one of the numerous different standards out there is the right standard? What's the right protocol to get wrapped around the D2D standard? And so all of this confusion, I think, has held up and slowed down the adoption of chiplets and heterogeneous packaging because of lack of clarity. So I'll share with you my thoughts in terms of different applications. Is it serial? Is it parallel? What's the right protocol? So first off, quickly some background. Serial is a traditional SerDes type of interface. It can be NRZ, it can be PAM, in order to get even more bits through a given channel. There's definitely some benefits when you talk about serial. One is you don't need silicon interposers to get very high density. Reason being, you can transmit over 100 gigabits per second in an organic substrate, and it doesn't use a lot of substrate area. So you can pack a lot of bits, get a lot of density. Obviously, with serial interfaces, you can drive today over 100 gigabits per second. In next 2-3 years, it'll be 200 gigabits per second. So you can drive high bandwidths. However, SerDeses are complex, so they need more time to become production ready in a process, which kind of goes against the whole time to market benefits of heterogeneous packaging. And as you go to higher rates, you typically need more equalization, sometimes error correction that introduces latency, and that detracts from the chiplet benefits. Now, if you look on the right side, in terms of parallel, this is much more like a DDR type of scheme. There's single-ended data, there's clocks associated with the data, double-edged clocks. Rates are lower, but you can you only have to send one signal, and it's a much simpler interface. As a result, because the rates are lower, because it doesn't use PAM today, it's very low power and it's low latency. It's also simple. I mean, theoretically, it's just a buffer driving one end of the chip into a buffer and a flop on the other end. So it's very amenable for newer processes, easy to adopt early in newer processes. However, if you want to get to this very high density, because there's so many signals being translated, you need very fine pitches on the bumps and very fine pitches in packages. That typically requires interposers. Silicon interposers are another material, increases cost. It's less widely used today, so prices are higher. In addition, we're in a SerDes space. You can route tens of signals and get terabits of I/O. On the single-ended parallel approach, you need to run hundreds, if not thousands of signals to get equivalent bandwidth. So it does complicate package routing. Now, in the next 30 seconds, I'll try to describe how I see these interfaces, serial versus parallel, being deployed. I think they both will have a home. I agree with a previous speaker. I don't think one will win versus another. Serial, I see being used as an interface for I/O. So the same way some of us older guys remember the north bridges and the south bridges of PC architectures from 10, 20, 30 years ago. I think in terms of chiplets, I/O, as you see in the top part of this diagram, connectivities from processing chiplets to I/O chiplets, I see serial interfaces maintaining themselves there. Switching, optical, those types of interfaces will benefit. However, when you talk about interfaces to memory and interfaces from compute to compute, that's where I see trends driving parallel interfaces more and more. Now, there are multiple standards. And how do you interface the NOC into these interfaces? You know, certainly PCI Express, CXL tend to be one path of interfacing the NOCs. But what we need to do as an industry is drive towards more standardization, answer these questions via specification, be able to support multiple different types of D2Ds to deploy these products, and ultimately grow the entire ecosystem, whether it's I/O chiplets, compute chiplets, package design, interposer, in order to make adoption and integration easier. And that's what we try to do here at AlphaWave. Thanks, Alan.
Thank you. Thank you, all presenters there. So we're now entering into a Q&A discussion session. So let me just move so I'm looking at you guys.
So Alan, while you're moving over to that section, I just want to remind all attendees that if they do have a question for our panelists or speakers, they can enter that into the question box. It's should be on the lower right of their GoToWebinar tab.
Yeah, and I guess I'll see the questions pop up, but whilst we're waiting for some questions to come in, I've got one. So I think, if Manuel, if you can turn your camera on so everybody can see the four of us.
I believe I am on. No. No.
Yes, you are. Okay, so thanks, guys. Interesting. Manuel mentioned, one size doesn't fit all on the I/O side. Rishi touched on it, and Tony's just gone through the differences of serial and parallel, and that there's actually many different options even in those two domains as well. When we look at an adoption perspective, I've got a few grey hairs. Go back to the 80s, we had something called TTL, and we had real chips, not chiplets, and everything was one bus. So everything connected to everything, and it seemed to be quite a wonderful place. Obviously, the power side is another dynamic here. Everything was 5 volts or 3.3 volts, and so I see very much analogous to those days when we had these pieces. We're going back. What's new, what's old is new. And I'm wondering if we can learn from that. What concerns me is to get adoption, to get this kick-started. If we have a proliferation of I/O standards, and I'm a designer and I want to make my own chiplet and I want to get some business in the industry, which one do I choose? And so should we? I recognize the need, but there's this idealistic perspective of idealistically is parallel for this and idealistically is serial for that. But is there a way to should we start somewhere and say, hey, look, let's start with this and standardize this? And should we focus, when we say an industry standard, should we focus on the entire industry, like tier 1s, 2s, and 3s? Because at the moment, this is the purview of only tier 1s. This is such a complex world, this chiplet world, what we see out of the big companies right now. So if you guys can comment on that, that's how do we kickstart this to actually get the business moving and starting to adopt chiplets?
So maybe if I can start off. Number one, I would say the standardization doesn't just conform to one particular deployment. Because the chiplet, for example, if you use for networking application, your criteria is for bandwidth on the beachfront. You want to send in a lot of data, terabits of data. When you talk about chiplets for CPUs, you're looking at latency, low power, and also a kind of more on the bit error rate, because there's more stability and sensitivity with that application. In networking, you can still afford to lose some packets. So in those two criteria, the fundamentals 101 of IO design completely changes. And even within the ODSA committee, we have basically the bow with a bunch of wires, and we have open HBI, which are addressing these two different verticals aspect of application. So what we are requesting, or what we are targeting here, standardization of both the schemes, because it helps the industry. There is no one universal chiplet based PHY which will meet the or bridge the gap of these two SOC requirements or industry requirements.
Alan, I'll step back. I think standardization is certainly necessary, but I don't think it's essential for what I describe as the democratization of chiplets, okay? I think there's still a lot of uncertainty in customers. Are chiplets and heterogeneous packaging economically feasible, right? Can I be competitive if I go down this path compared to the traditional monolithic path, both from a price and a power perspective, okay? I think what's essential in order to enable more widespread adoption of this, we need to ultimately answer that once and for all. What is necessary in order to create competitive multi-die products in terms of price, in terms of testing and test times, in terms of power efficiency? I think if we can achieve that, everything else, the motivation will be there to solve everything else. Standardization, widespread adoption.
Yeah, I think we've got to start somewhere there, right? That's the only thing. In terms of maybe IO is a place to start, because that's where everybody else comes in. Manuel.
Yeah, I agree. I think. I mean, we talk about. So if you look again at the IO, we talk of, when we talk about parallel or serial or other types of interfaces, we tend to say, as you said from the beginning, Alan, parallel is for interposers, and then serial is for organic substrates, things like that. That's perhaps not the way to look at it. Is more like Rishi was saying. You look at application and what the application is, and actually Tony also mentioned this, and that's where the the preferred, let's say, type of interface comes along, and that's what standardization needs to follow. I think standardization is needed. It's not just optional for an open market to thrive. Otherwise, yeah, there will be no communication between the different parties.
And everyone tends to focus more on the electrical interface as serial or parallel. What I think is even more confusing to folks is on the protocol layer, because there's even less work that's been done there, even less specification. So I agree, at the end of the day, it needs to be a knock-to-knock interface, but using what protocol? And I see customers that are completely lost as to what to do there. And again, until we solve the entire connectivity solution, we haven't democratized this, because only a select few that have already figured out, the Intels, the NVIDIAs, the AMDs of the world, will be the only ones being able to deploy these types of products.
I've got some more questions coming in here, thick and fast now, actually. So first one, will EDA vendors move to become chiplet vendors since they sell a lot of IP?
So by nature of the business, the EDA vendors will actually accelerate the deployment of the chiplet-based design. It can be IP, it can be the tool flows, it can be the testability aspect of it, but they facilitate the industry, they facilitate the customers, rather than customer taking the whole burden of doing the design. In whatever aspects of this engagement model, the EDA vendors will participate and kind of make sure that they provide the right level of support to the end customers or to the industry.
Yeah, I think go ahead. Okay, so I think the EDA vendor is an enabler of the design process. He brings in the tools, or maybe the IP as well. Does he can do the design as well? We'll see. I mean, there's no. This is an infant industry. We'll see where it takes us to. But I strongly see that today the EDA vendor is an enabler. Is there to help the other companies get their designs out in an efficient and cost-effective way.
I think it's particularly contaminating to have EDA and IP suppliers sell chip or silicon. At that point, you're potentially competing against your own customers. I think those that have been successful over the years have stayed in their swim lanes and not gotten into their customers' swim lanes. So okay. We'll see how it evolves.
Yeah, I agree with Tony. Normally, the EDA vendors don't play in silicon manufacturing, but they can facilitate and accelerate that deployment, not into manufacturing of the chips. Yeah.
Okay, next question we have on power distribution. Onboard power management in each chiplet limits system efficiency. Since the supply to the package needs to accommodate all the heterogeneous chiplet requirement, isn't a programmable PMIC chiplet with DC to DC converters on board to service all chiplets a better choice? Besides efficiency gains, higher input voltage, lower current, and number of bumps, you can also manage chiplets supply, ramp up, ramp down, etc., as you would do in any board level system. I guess so. The power. Go on.
I'll jump in for sure. I'm involved in some programs where stuff like this is happening. So absolutely, all of the complexity that has typically got into PCBs to manage multiple discrete ICs and the value that that's delivered. Now, as you build heterogeneous packages, which are little ecosystems of silicon themselves, things like local power management that can drive the chiplets makes a tremendous amount of sense.
Okay, one more here, unless there's any other comments. Hang on, this is scrolling fast and I can read it. Organizer, no, sorry. Excuse me a minute. No, sorry. Is there a business for small companies in this market?
So look, I'll jump in, and then obviously I'd love to hear from others. I think our whole industry has been built on innovation, right? When you look at Silicon Valley, innovation is what's driven us. Alphawave, we are a smaller company, but we have grown quickly in connectivity IPs. And so I tend to believe wherever there's innovation, that's where success will ultimately be. Okay, this isn't a game where just because you're big, you win. You constantly have to innovate. And the minute you don't, there's someone there ready to take your space.
I agree with Tony. Basically, there is a lot of food on the table for small or big companies. And I think so sometimes being a small is a little bit more advantageous because you are laser focused on that particular technology for survival or for being success. You're more hungry, let's put it this way. Right. So I would say that I would not discount it or say that it's small or big at this point.
I agree. I mean, I think and that's what we are trying to enable here. It's those small companies to have success in this space. How we can do that? How we can make that happen?
I think that's a big. I think it's a big question that we do need to think about it from that side when it comes to standardization for sure. Next question is: big companies will build their own chips and control their own interface and interconnect choices based on their internal needs. This is already going on. Others might buy them, but that's just a small extension of the current known good die market. I don't see a driver that will break this out.
So going back, I think the driver needs to be cost benefits or business benefits, right? Clearly the big players, again, I'll highlight the Intels, the AMDs, the NVIDIAs of the world, they've seen a benefit for their products, and And because there has been no standardization, they've driven their own paths. And perhaps they'll forever drive their own paths until there's a cost benefit or a business benefit for them to leverage a thriving, successful ecosystem. So rather than build, let's say, their own co-packaged PMIX or build their own co-packaged IO chiplets, they buy it off the shelf. And so, again, the way to democratize this is to deliver the same, can we deliver the same business benefits to others as the larger entities have realized?
Okay. Anyone else?
Yeah, I tend to agree with Tony on that front of the discussion. And the other aspect of it is these companies basically deployed the technology or their ways of doing chiplet because there was no standardization. There was a lack of a forum like this 2 or 3 years back. But looking forward, I think so they need to look at it. How can they leverage? And it's a beneficiary not only to the industry but even to them, because the moment you standardize it, it basically has a direct impact on the cost. And the standards are evolving. The feeds and speeds for the future generations are also changing. So they need to make changes to their design too to scale it to the next node. And also there's some learning associated with it where they can provide us the valuable inputs as to what were their gotchas when they were deploying these type of platforms. So it's a win-win for both. And I think so that's what the ODSA committee members are trying to get, basically inputs, feedback, and expert advices from folks who have already implemented it or have been through this particular journey.
Okay. I'm conscious of our time here. Ravi, are we into coffee break yet, or should we break off for coffee or continue the Q&A?
So actually, Alan, what we are thinking is maybe we'll take a coffee break now, and then we can continue the Q&A for the folks who wants to stay. But I think we can go into the official coffee break so that we'll give everyone some breather in between.
Okay, if you want to put the coffee advert up while we're continuing to chat, that'd be good.
Michael, do you want to put it up?
I'm happy to do so. Ravi, would you like me to put those polls up just for a moment first?
Yes, yes, yeah. So we have some poll so that we can get some feedback. So 2 questions, 1 minute each.
I've just seen one of the.
So Michael,
all right, thank you everyone. We'll go ahead and close this poll. Ravi, would you like to share the results?
Actually, let's show the second question first.
Oh.
Second poll.
Whoever wrote these has a good sense of humor.
Yeah, I was thinking that.
All right, Michael, if we are 1 minute mark, maybe we can close the poll. And you want to show the result. So right now I want to announce that we are at a coffee break. We will reassemble at 9:40. So it's about 7-minute break, but those who want to stay, we will still take some of the questions which we are getting from the audience.
Okay.
2023.
Makes sense.
But we still had 14% saying, nah, keep dreaming. That's interesting.
Yeah.
Yeah. So this is overwhelmingly 80%. Yes. Okay. All right. Sounds good.
Okay. Well, thanks. If you guys are good, we can keep going through some of the questions. There's a couple more here. This one's, at what technology node does it no longer make sense to develop subscale brackets, mobile phone, server, PC devices? Subscale devices.
Subscale.
I'm not entirely sure what that question means.
Maybe the intent was monolithic, I would think.
I would guess.
Yeah. Manuel, do you want to jump in?
Oh, I can. So I think we should not underestimate the need to move designs to more advanced technology. So I think monolithic designs will continue there, and there will be a need for them in a number of advanced applications. Now this will have to be extremely high volume. So mobile is probably one of them where things will continue moving on monolithically into more advanced nodes. Where does it stop? I don't know. But we've said that it would stop for many generations, or somebody has said that it would stop for many generations, and it has not. So I think it will move on. Now it's so high volumes required will probably be so high that it's not for all, and that's where chiplets and this alternative way of doing systems becomes interesting. Again, we need to prove the economic value of these for the companies who are involved, but that's the direction, I think.
So I remember speaking to a guy in a fab a couple of years ago, and he said back in and around 10 and 7 nanometer, they're no longer stacking transistors, they're stacking electrons, okay? And it's the fact that, the laws of probability tend not to apply too well when, the number of electrons gets smaller and smaller. And that's clearly what's driving the defects in the economics. So if I had to put a point, I'd say 3 nanometer, I think is going to be a key catalyst for these types of products, okay? Because we're stacking less and less electrons. And at some point, the economics start going in the other direction.
Okay, so just in terms of the questions, I've got one. In terms of, if we look at the flavor of the questions, they seem to fall into 2 camps, really. There is this, how do we get this adopted? Where does it start? Is this really going to happen? Is it the purview of the big guys? I guess the way I see it is that, yeah, the big guys are going to continue to do some great stuff with the likes of HBM and they're more, getting over the reticle limits, etc. And that's the purview of the big guys, and it's driven by big markets. And I struggle to see the need to standardize that because they just do their own thing, and the market is big enough for them to do their own thing, or they partner with the fabs that specialize in this. But then at the other end of the scale, we do have the desire for smaller companies could definitely benefit from this, and that's really where I think standardization makes sense. So should we should there be an effort to demark what is in the big boys camp, so to speak, and what is for the rest of us? And should the efforts of the ODSA and the chiplet standardization at least start at the more accessible end and not try to boil the ocean and solve everything?
My view, Alan, is I think standardization is a great thing. I think it's a key barrier that needs to be removed. I think we need to make it more accessible for everyone else. I don't think we should try to service the big guys, but rather service the problems. And if the big guys want to get behind it, they will. If they want to do their own thing, so be it. And when I look back, let's say over the last 20 years in terms of industry standard bodies that have been successful, I think something like PCI Express has been remarkably successful. Okay.
Right.
It started off with the big guys, but it's become so widely deployed. It's, many interface standards have died over the years, and PCI Express has remained, one of the last few standing. And so if we want to replicate a standardization process, I would look to that playbook to see what we can learn from it in order to get D2D interfaces more standardized.
Right. The big issue here is the power of the interface, right? I mean, it's trying to drive the power down into the sub-picojoule per bit domain. If we look in a server today, we're in the 5 to 10 picojoule per bit to get from the front of the server to the back of the server in a 19-inch rack. And our industry seems to have gone from the 19-inch rack straight down to tiny die on a substrate. Is there a middleman somewhere here where maybe we could reduce it to small modules and actually have chiplets on pluggable modules? And so that is, so for instance, in your world, Tony, with silicon photonics in the rest, would it be possible to maybe get to miniaturized QSFP subtype?
Yeah, that is a thing. I mean, there's a whole area called
it's called the direct drive optics also, right? The direct drive optics.
Yeah, integrated optics. So, and with integrated optics, it's that concept. It's pluggable modules. So the way you reduce power is you bring, you bring the interfaces to the outside world closer. You drive less copper. You go to optics, which inherently consumes less power for transmission over equivalent distances. So yeah, there's a lot of work, a lot of investment happening in that. I think when you see 50 terabit, 100 terabit switches come to market, that will be, that'll be the driver for a lot of this type of integration.
So maybe I/O is the first sort of place where the wider standardization could work first, as opposed to like standardizing other areas.
I think the standardization of the IOs for the optical connectivity, there's been so much of work done on silicon photonics, and I'm pretty sure even DJ was part of it while he was working at Infinera with a similar background and at AMCC. Where the rubber hits the road is the IEEE and the OIF, both of these, or the both of these committees, they are never in sync. Always remember that IEEE is at least 5 years ahead of OIF. And the reason is very simple. OIF is more commercial. It's driven by the likes of Avago, Finisar, and the folks who make optics. They want to skim their investments much at a slower pace than the IEEE. You see 400 gig standards coming, optics of 400 gig are not there through 400 gig. You see 100 gig standards coming, optics was sitting at 25 gig. Always there is a lag between the OIF and the IEEE because of the nature of the business. It's not that they don't want to move forward. All these guys want to, skim their investments, their inventory, and that's how it works. Silicon photonics has a second set of challenges, which is the standardization on the lambdas, because now you're dealing with something on silicon, so there has to be a deviation from the standard optics. That kind of hampers the deployment, because then it becomes a little bit more proprietary when you're operating at a different lambda of 450 or 700 mm compared to a standard lambda going on the optics. Plus the yield efficiency of integration is another challenge. But the industry right now is driving towards that. As Tony mentioned, when you talk beyond 25 terabits of switching, then folks are basically looking at options to take that risk or standardize that in a different tangent where it is universally being deployed by folks who are in that territory of 50 terabits.
Hey, thank you everyone. We wanted to start the next session. Okay. So thanks, Alan, for moderating, and thank you all the panelists. Moving on to the next section, which is the build portion, where everything gets created. Here to introduce this section is Andreas. Andreas, take it away.
Hi, so I'm Andreas Olsen, and I'm pleased to honor to moderate this panel with Elke Bergman from AC and Maximum from Samsung, Wigan Mills from Teradyne, and Tony Prasad from JSET. So I'm going to start off with a couple of slides, kind of to ask some provocative questions and try to set the stage for the others to present. So as many have said today, today the chiplets is the domain for the big players. Clearly, there have been many successful chiplet products produced and manufactured today from companies like Intel, AMD, and Xilinx. There's one unifying factor there in all those efforts. The number of players or owners of the devices inside those products is between 1 and 2, I would say. When you have HBM, you're going to take in a fairly well-defined, JEDEC standardized module. But beyond that, pretty much all the silicon comes from the big players. And if you compare to what I think the vision for ODSA is, you see that there's going to be many, many players. You're going to have something more like what you have in the PCB ecosystem today, where you have a 3+N type game of trying to produce the final device. And that's, in terms of an economics perspective, that's a much, much more complicated game, because it's sort of a zero-sum game. You have to negotiate over who's going to get the margins, who's going to own the yields, and so forth. So economically, it becomes infinitely more complex when you've got 10 players than when you have just one owner. So since we're talking economics, I haven't seen anybody put this up, but I wanted to sort of a little bit bravely put up real economic numbers here. I think most people don't want to talk about margins for their companies, but if you look at the different pipeline stages, right, in manufacturing an SoC device and a system today, we start with ideas at the IP side. Ideas are made out of air, so they're very, very high margin. Something like 96% for IP, but it's a smaller market. Now we start manufacturing foundries like Samsung, TSMC, Global Foundries, Intel, and now you're building real things. The cost goes up significantly, margin goes down. This is hard work. You start to have to worry about yield, and cost per unit matters, right? You're not building air. As you get into assembly and test, the demands on yield go up. When you talk about design, everybody understands that it's design specific. The larger the die, the lower the yield. With assembly and test, the demands on yield are usually very, very high, something on the order of 99%. And the margins tend to go down on a per unit basis. And then as you go up to PCB assembly, you're talking about even more devices, more cost per unit, and the margins go down. So these numbers are going to set the stage for who can actually create this ecosystem in terms of R&D investment, and also who can own the yield fallout from the margin perspective. So I'm just going to leave this here and come back to it maybe with some discussions, and of course happy to start discussions from the audience as well. So if we just one more slide to kind of talk about the wonders of manufacturing that is Moore's law, right, and what we got used to over 50 years. If we look at yield, doing advanced technology is hard. Right? It always has been, right? It was hard at 180, hard at 130. It's incredibly hard at 7, 5, and then maybe even be impossible at 3 nanometers. I mean, these are heroic discoveries and engineering feats that people are making, right? Now, of course, doing advanced technology at high volume, that's even harder, right? Because now you have to worry about yield, because if you can't hit the yield, then you can't produce the volume, right? At least not according to Moore's law. And so let's remind ourselves that if we ever want to see a similar kind of Moore's law extension We have to worry about volume. We have to worry about yield. We can't worry about one-off prototypes or one-off showcases, at least if we want to address the larger electronics market. So what I showed here was, was kind of a toy example. What happens when we start scaling up the number of chiplets on a device inside a package? If we have a $1 chiplet, and we start having 30 chiplets, you quickly find out that anything less than 99% assembly yield, it's going to be very hard to make a compelling product, and that's the reality of yield of multiple devices. So with that, I'm going to hand it off to Max, who's going to talk about his view of Foundry.
Okay. Thank you. So this is Max. Next slide. Okay, so today I'm going to talk about the Cube for enabling the Chiplet. So before I talk about a little bit about the Cube, I will say I will give you one simple definition of our Cube. So Cube is a device, more like an interposer device, connecting the small and large chiplets for horizontally and vertically. That's what it is. And then I'm going to talk about some lesson learned. We learned from memory. Okay. So as you know, the memory is in general in amount under the PCB board. But thing is nowadays people trying to have an advanced package called a package on package or 2.5D package or 3D packages. So you can see the old diagram here. But one thing is you may notice in this the type of new products, actually there's some innovation in the memory side. So memory guy trying to use sort of molded chiplet. So for example, in a pop case, then people develop reuse the LPDDR memory and then do the molding and then stack on top of the logic bottom package and then make it as a chiplet. So basically, this top LPDDR cannot be directly mounted on the board, and rather than then they mount on the package. The similar concept, they actually expand the similar concept, but with a little bit fine pitch, which is 55 micrometer pitch, which is high bandwidth memory. This package actually is molded as well. So then by having this one, then people can enjoy the 2.5D sort of a product based on the interposer. That's the one. But now this is what we learned from memory guys. And then now what are you gonna do for our say logic chiplet as well as a 3D? So the example, let me talk about example, then I can give you a little bit, I would say our view, I would say foundry view or package view on our foundry side. So we have a couple of examples of which we call the Cube examples. So Cube, as I said, this is more like an interposer device. But interposer, we can categorize into two. One is active interposer, then the other is a passive interposers like that, okay? So why we talk about active interposer on HBM Cube? Yes, HBM has a 4 high, 8 high, 12 high, and 16 high or DRAMs, right? But if you notice that at the bottom of those high, you see some buffer die that is active interposer. So then that active interposer enable the HBM Cube and help to have, we can enjoy 2.5D applications. So Samsung Foundry, we would like to also enjoy that active interposer. We call the logic on logic. So basically, we can have a bottom active interposer logic, and then we can stack more and more logic die on top of each other. But thing is, we don't have any limitation. We can stack I would say DRAM die or SRAM die or logic die or chiplet die, small chip, large chip, doesn't matter. We can stack as many we can. So that's why we developed the X-Cube. But so we're talking about these two, right? Active interposer. But things we still need the horizontal connections. That's why we decided to develop silicon interposer. But silicon interposer, always people talk about is it non-good or not. That's why Samsung developed the thinned silicon interposer. Thinned means we already do the TSV exposure, and then it's ready to call this is a non-good silicon interposer. That's how we call the iCube. Okay, and then the other one is, you know what, TSV is expensive. So is it anything we can do for without TSV? We call the TSV is non-good interposer. That's why we are developing our Cube, which is RDL-based interposer. And the last one is actually chiplet applications. So as you know, the chiplet, we need many different type of pitch and then different number of layers for the die-to-die or chip-to-chip connection or chiplet-to-chiplet connection. That's why our motivation is to develop some sort of a flexible pitch and a flexible layer count interposer. That's why we developed the embedded bridge we call the E-Cube. Okay, so all this example we call that is a cube. So we think as a cube gonna help or enable the chiplet business. But there are still many technical challenge and business challenge. I just list up I would say in the three. I think in the previous presentation, people already addressed all kinds of issues. For example, heterogeneous integration with a boundary logic A and B or boundary B or A and B, something like that, and memory 1 and 2, blah, 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 many kinds of memory suppliers, and also D2D IP designers, alpha and beta, and also lots of decoupling capacitor component in the package. So how are we going to integrate all them together with the OSAT and also IP partners? So that is still, I think we need to address it for the enabling the chiplet business, okay? And on top of that is our headache. Actually, since there's so many combinations, so many variables, I think from our side, we gotta confirm, okay, we gotta confirm the PPA, power, performance, and I would say the hertz, and the size of I would say millimeter square. We gotta confirm it by developing a lot of test vehicle, okay, for the thermal and mechanical integrity and also signal integrity, power integrity, and then finally form factors, because package size is too big and too small, or is it can be fit or not, how can we accommodate many other chiplet dies or something like that. So we have to develop so many test vehicles. I think in this OCP and ODSA, we will talk about all these test vehicles as well, I think. And then last problem we think is a known good chiplet and cube. Okay, I think that the ownership of this chiplet and cube known good thingy, I think it's still we need to talk about it. Okay, so Andres, so that's my.
Okay, all right. Thank you, Max. That was great, and I'm sure we'll come back with questions for you at the end of the panel. Okay, so now moving to the assembly and test with Elko.
Elko, you are on mute.
Good morning, everyone. Sorry about that. For this section, all three of us, myself, Swami, and Reagan, will present some of the slides. So I'm going to kick it off with the first one. Go ahead, Andreas, to the next slide. Just to set the stage. So, we're here talking about the business enablement for an open chiplet ecosystem. And we've talked a lot this morning already about this transition that you see on the left-hand side, where we've gone from fully internally designed monolithic ICs to ICs with third-party IP to disaggregated SoCs, but still largely controlled by vertical players. And what we're now talking about is how do we move to a virtual SoC that could be comprised of not just internal devices, but also third-party IP chiplets. And I think when you look at this model where you have multi-sources coming in, you also have to look at what's been happening on the system side. So we've, over the last couple of decades, seen a lot of miniaturization taking place, moving from large motherboards to high-density motherboards to SIPs, as we've seen in some of these wearable devices. And in a way, what we're doing in the middle is very similar to where that trend is coming from the right-hand side. So if we think about the business enablement, there are technical challenges, of course, related to EDA and how do you put these pieces together. We've talked about standard interfaces. There's the design piece of how do you take GDS files and merge those with package level MCM files with system level Gerber files and get those design tools to talk to each other. But another big factor is just the business model itself. On the left-hand side, when we look at traditional packaging, it's a model where the silicon is consigned, the packagers add some value, and as Andreas showed, our margins are more limited. and then we ship that product back to the chip supplier, and they sell it to their end customer, and they take responsibility for the product. When you come from the system side, you've actually been buying known good, fully tested packaged parts. There's data sheets available on how to interface them with each other, etc. But as they've moved from right to left towards higher density solutions, they're facing some of the same challenges. And I think the opportunity is for us to learn, how do we leverage the best of both these business models to come up with a model that's going to work for this third-party virtual SoC type model. And that's really what the point of this panel is going to be, is to discuss those issues. So Swami, I'll turn it over to you.
Oh, thanks, Elko. So Andreas, if you can please share the next slide. Yeah, so to set the basis as to, we have this highly scalable process flow, or the business flow, so to speak, that's existing today, has been there for a while. And we felt it's important to understand again, what are the key components that's driving the success today of the existing model, and what it would take us to make an adaptive model for the chiplet industry to thrive. So today, everything starts the business process for us. For the build part, is from the RFQ to the point of shipment. We look at various technology options with the goal of cost in mind and the scalability of the solution. There's a plan of record, and all the elements of design come together. To the fab, as Max mentioned, they have to go through a lot of testing to ensure that you get a corresponding silicon that will enable the assembly. The test is a very critical part that comes at the wafer sort, or the final test, the system level test. Then you have to qualify this, at a package level, at a system level, and then you enable the whole shipment. And the various assumptions today, the silicon and the memory packages are consigned because there's a liability aspect. Substrates, very high-end substrates, are also consigned. And passives can also be consigned. Over the last few years, there's proliferation of a lot of passives, capacity constraints, etc. And the process flow is, pretty well defined as to who owns what. Going to the next slide, please. So what we did was we looked at three different, high-level boxes, so to speak. The product ownership. Where's the PO going to come from? Is it from the end customer or the semi provider? Who's going to take the liability? There's so many elements coming together. Then you look at the technology box, the different solutions. You can go to the interposer solution, like Max was mentioning, and there's a cost aspect, but you can pick the heterogeneous option, the fan out, or the substrate option. Again, it comes down to the cost economics, then how you design it for performance and all the thermal considerations, the space, the PPA, and the test methodologies. Regan will speak to that. And you have to qualify this technology for high volume application and the time to ramp. And coming to that is a supply chain. The OSAT would be the integrator probably for this chiplet model. How do you enable the sourcing? What are the different commercial engagements? So these are, all the answers are not available, but these are the aspects. And we did the poll. I think the business workshop should be continuing going forward, because there are a lot of things that we need to address in order to realize the chiplet business model, so to speak, in a high volume framework that we are used to today. So with that said, Regan.
Thanks, Swami. Hi, I'm Regan Mills, the Vice President of Marketing for SoC Semiconductor Test for Teradyne. This is actually my first OCP forum, and I just wanted to thank the leaders for the opportunity. I want to start by putting a fine point on some of the curves that Andreas put up earlier. One of the business challenges for widespread adoption of any technology is the ability to reach a compelling cost structure. And many promising technologies have failed to reach scale because of that. So if we look at the cost structure of a chiplet solution, it becomes apparent that the value of quality is making a huge shift. The value of quality, what does that mean? Because we usually don't talk about it that way. But the way I think about the value of quality, you can quantify it by the cost when that quality is absent. In other words, if you're missing the quality downstream, what's the cost of incurring that downstream? So let's first look at a monolithic solution. So you've got one die in one package. The economics of quality take basically you can basically look at it as the cost of packaging a bad die. And so with that, to a first order, you basically have a 2x cost increase. It's kind of on that order of magnitude versus finding the failure upstream. So it's significant. But if we look down below and we think about a chiplet environment where you have a completely heterogeneous design, multiple die coming in from multiple sources, you're not only accumulating the yield loss at final test through the test escapes of the many die, but you're also multiplying that by the accumulated cost or value of all of these devices in that final package. So this multiplicative effect of yields and cumulative device costs, this is what creates a situation in which the value of quality is absolutely crucial. Now, there's at least one order of magnitude in the cost of a failure at final test due to these effects, and that was what Andreas's curves showed. Now, I think we've talked about it in various forums, but KGD or known good die is really the answer that most people quickly jump to. But the reality is that it's really not known good die. It's about what's good enough. And good enough is a function of the total system cost model. And chiplets are going to put tremendous pressure upstream because the cost model is going to shift here. So unlike PCB assemblies, another point is that physical repair methods are also quite limited once you're in a chiplet environment. So reason why the cost of function is also going to be different in a chiplet environment. In terms of other considerations, one way we might be able to get around this is sort of an intermediate test methodology to sort of catch escapes earlier through a partial build. That'll also be fairly expensive. Max alluded to the concept of a sort of an intermediate assembly process where we have cubes that are being purchased. So almost the concept of a multi-die chiplet, if you will, which will work for suppliers that are in a position to supply all of the IP and silicon in the stack. So there may be a hybrid solution there. Andreas, if you could proceed to the next slide. So now if we look a little bit deeper into the detailed considerations, it rapidly becomes clear that we can't completely talk about chiplet manufacturing economic considerations without identifying some of the technological challenges that are intertwined. So on the previous slide, we looked at the accelerator on the importance of KGD, but we should also acknowledge that what's been classically an IP model in which the IP is targeting the integration in a monolithic piece of silicon, this is different in a chiplet environment. So companies that have standardly really supplied soft IP are moving in a direction of supplying physical devices. And by moving to that chiplet environment, it's actually different in a number of ways because these devices, when they're on a monolithic piece of silicon, there are a number of considerations. They're not designed to be tested. They're not designed to be probed directly. Physical layout hasn't been done. So, and things like ESD structures are uniquely required when you're talking about shipping parts and handling parts. So that's a pretty big departure from the way IP companies have typically been thinking. So one economic result of that is that we're going to have to think about a little bit of incremental cost associated with these chiplets, really for the purpose of ensuring that test and not packaging, but handling of the devices in the substrate. Those costs, there's going to be a little bit of incremental cost to ensure that those processes can be effective. So looking, thinking about this KGD problem, there's another element here, which is the substrate itself. You can kind of look at the substrate as one of the components in the whole stack. So incredibly high yields are also required at the substrate. And for some designs, that may not be a problem, but when we're dealing with some of these high performance designs, the interaction between the devices, the substrate, and the receiving device, that whole system is going to need to work highly reliably. So, and we're going to need to be able to test that entire stack and that entire without pure functional test, which may be required, but also having a test standard. And I think the technologists have done some really good work in advancing IEEE 1149, through the years to the current 1838. But if you think about any standard is not sufficient. Having a standard also requires adoption. Once it's adopted, then it actually could be a real solution. And I think that standard is probably sitting in a place where it largely solves the interoperability test problems that you have on the substrate. Now, there are some additional specific challenges when you get to high-speed interfaces that have to be addressed in order to make sure that the overall economics are manageable here. High-speed interfaces on chiplets are generally designed to drive a few millimeters to the next die. They're not designed to drive a prober interface. And if you look through the history of high-speed interfaces, there's definitely proven models that as long as you can achieve process stability, a combination of process stability and predictability, combined with on-die loopback, the economics are manageable. And that's something that's been happening for years. And I think that's going to be the future in that area. But I would say that chiplet designers should also really look at the HBM world for some lessons learned. There are fault-tolerant interfaces that can be corrected, as well as the usage of sacrificial test pads or test bumps to ensure that the active probing doesn't actually induce defects through the test process. So I think HBM has actually been a trailblazer here, and we should really look to those examples. Not all of the lessons are going to cover all of the problems, but some of the harder ones have been addressed. And a final thought is just around the substrate itself and getting to a high yielding solution at the end. I think the necessity of a comprehensive design environment in which design margin can be ascertained while bringing multiple die together, combined with a substrate. So you get a die from one supplier talking to a die from another supplier over an interface, a substrate that's being designed by a third party. That needs the ability to ensure that we can get to a highly predictable design margin. Otherwise, the economics are also going to fall apart once we get to final test. And the other thought is that most of these complex designs are going to require some level of system level test. And system level test can be incredibly long and expensive unless it's reasonably targeted. So the other purpose for having this design margin environment is to be able to identify the places where you want to focus your test. So with that, I'll turn it back to the next presenter.
Okay, so let's start the question part of the panel. So I will start with a couple of questions, and then we'll move on to the audience questions. So I think that the first question I have, and then maybe on other people's minds as well, is for chiplets, will we ever see the type of ecosystem we have for IC, right? Where you can go to a distributor like DigiKey, Mauser, Avnet, Arrow, and so forth, and buy chips with data sheets and expect them to work, right? Failure levels like 10 parts per million or 100 parts per million, something along those lines. You know, do you see that happening with chiplets ever? And you know, what are some of the blockers to get there? So this is for the panel.
Andreas, so I'll take a stab at that. You know, I think your chart accurately depicted that it's necessary for us to get to that point. So it's not a choice of whether, but when and how. I think from a technological standpoint, largely the barriers are all things that can be overcome. I personally don't see from a design or from a test standpoint anything that prevents us from getting there. There is a mindset, though, from a business environment of thinking about companies that typically would embed IP and mark that up as part of their business model. Getting an industry comfortable with the de-embedding of the IP is something that I think does have to be overcome.
So, Andreas, if I could respond, you know, will we ever see it? I think to some extent we've seen it a little bit already. I mean, you can argue whether HBM is a chiplet or a product, but I think that's the case. So I think there are some. We'll see some initial cases, whether it's with memory, with SerDes, whether it's with maybe FPGA accelerator blocks, tiles. I think we can start to see some pure IP chiplets emerge, and then over time that portfolio can grow. But I think the need to try and bring down the SoC design costs to have some level of IP reuse, and also to have that IP really be silicon node performance and cost optimized will drive the industry towards that. Is everybody going to adopt that? Probably not. I think, you know, we have a few leaders who are pushing vertical solutions, and that's what it's going to take to have companies like that help pipe clean this process. But as we see where IP chiplets make sense, I think we will see an ecosystem emerge of third-party IP chiplets, the same way we saw soft and hard IP providers emerge in the late 90s and into the 2000s, and SoC designers adopting that third-party IP.
Do you? So if we talk about the you know, the big question, you know, yield and you know, bad product fallout, any thoughts or clarity that you can provide on when something goes wrong, who owns the failure?
So that's why our current process, we have qualification. We deem a plan of record a device that can be scaled, and we invest to ramp it up in production only when it satisfies all the qualification criteria. And yield is a big part of that equation, and that's where the testability that Regan was talking about, where you focus on. So we have a good measure of success even before we start. Now, of course, if it goes to the field, and your question is what would happen, typically the industry structures, you get a third party, and we do the analysis, and where if it is a die issue, if it's a substrate issue, an assembly issue, that's where the ownership comes in. And of course, the reworkability, it is possible, of course, depending upon the type of issue. But you start with an effective product that is fully qualified, and what are the yield fallouts, etc. Very rigorous qualification process. That's how I would address that.
So
if I could
so
comment.
maybe, yeah, go ahead, Ilko.
Yeah, I was just going to say, I mean, if you think back to the first slide that I put up, right? At the system EMS level, the system level, we've been designing systems just on a larger scale than a system in a package or a system in module. And the way we've been able to do that is the incoming devices are all fully tested, and they come with a certain level of yield and reliability assurance. And for this chiplet ecosystem to work, absolutely, we're going to need to have something similar with those chiplets. So that's where the test strategies, known good die, known good chiplets come in. I would disagree with Swami. I think when we're doing this level of virtual SoC integration, rework is not going to be an option. So, the chiplet suppliers are going to have to stand behind what their yield levels are going to be. And then the product designer, whoever's doing the integration, the product owner, will have to make an economic determination based on how many chiplets are going in and what the individual yield levels are, whether or not that can be a viable product based on the resulting yield. And I think that's one of the big challenges, and Regan pointed that out in his slide, is, you're going from traditional packaging where you have, the foundry yield, the package yield, and the final test yield. Now you're taking that to the nth factorial, so the yields can collapse pretty quickly if you don't have a high level of coverage and assurance.
So yes, I guess one of the big questions is, what Regan was mentioning as well, right? We can get pretty good confidence in doing a die level testing, but if we compare that to the IC suppliers who sell to the board vendors, and we're talking about final test. So do we have any kind of idea of what's the coverage that we can get on a per die basis as compared to final test? How close to the final test quality can we get on the die?
So Andreas, in most cases, we can actually we can get the test coverage. Many complex devices today actually ship, that after only one insertion, just a bumped probing insertion. So I think the test coverage per se, to a first order is not the bigger issue. However, test coverage is an exponential function of the time that you're putting in order to find those last defects. And this, the curve that you put up that really shows the cost impact, right? The ability to move from 99% to 99.5% coverage. That's an economic proposition that we're going to have to look at on an individual device basis.
Yeah, I think it's, I think
do I think it's achievable? I do think it's achievable, certainly in structural devices where the test coverage is highly calculable. That I think is quite difficult. The place where it may be more challenging, areas like analog designs where customers are used to developing a test plan and kind of iterating on it. There may be a situation where based on downstream escapes, you need to add test coverage. But I don't think it's an equipment issue as much as a test plan issue.
I think there'll also be some trade-off, right, between what's the cost of that test coverage versus keeping the cost down and maybe having a little less test coverage. So I think there's quite a bit of modeling required. But Max, just a question to you, right? If we think about the HBM case, you're layering multiple layers of DRAM onto a control die. I'm sure Samsung has gone through quite a bit of analysis of how much test do you need to do on each of those individual layers and how much do you do at the aggregate piece? Any comment on that?
Okay. Can I give you a general comment? Let's say to my view, yield is the more like a couple of groups. I would say the fast fail kind of yield loss, basically in open and short time. And the other one is a parametric yield loss. But some of them is not under those categories. That's why people developed a lot of tools, for example, visual inspection tools, okay, and also many different kinds of tools, okay, because sometimes you cannot physically detect. The reason is silicon by itself, actually you have one planar surface, then you can visually inspect it entire surface. You can detect where the failures are. But when you talk about chiplet, this is more like in buildings, okay? Basically you are in the city and you have a tall building, short building everywhere. But thing is on top of all the city, and then you can detect the failure. It's very hard to detect it because different depth of, I would say, the visual length. Then because of that, there's a teeny tiny issues here and there. That's why I believe in order to enable the chiplet, I think we need I would say, improve those, I would say, the visual inspection as well as a fast fail kind of testing systems, okay, at the micro bump or even below. Okay, what I remember is HBM is still around 55 micrometer bump pitch level. But when you talk about the chiplet, it's already down to 10 micrometer below, which means we need some sort of tool we can detect some particle or some issues, some teeny tiny, maybe smaller than 1 micro. How are we going to detect those, I would say, bomb in the chiplet? That's why I think for us, actually, the chiplet, I would say in our case, is we are now dealing with a more aggressive problem than HBM. But HBM problem, I think already all the equipment supplier vendor, they already know what to do, which means we just learn what to do. But thing is a chiplet over here is logic chiplet with a memory chiplet. I think we need to address all those problems. So that's why our view is, you know what, let us deal with the problem by developing the cube. Cube is, we can use this cube technology, I would say packaging the single die or multi-die. But thing is, we don't know how many die we can put them together because I have a tall die and short die or things. There are so many variants. That's why we decide to develop so many different type of cube technologies. Okay, so but maybe I cannot give you a clear, I would say, thing about our HBM experience, but I believe while we learn, all equipment partner already learn from HBM, I would say, the chiplet. Okay.
Okay. All right. Thank you, Max. All right. So I think we're going to go on to the questions from the audience now. And so here's first question for everybody. You know, what new manufacturing and metrology systems will be required to enable a viable chiplet assembly ecosystem, particularly as interconnect pitches and interconnect density increase? So, for example, going to 55, 35 micron pitches, maybe someday even down to 10 micron pitches.
Maybe I already mentioned about that one, but I think a couple of days ago, I saw some, I would say, the I would say the use. Actually, those guys also claim they can handle the 55 or sort of a bump pitch part, which is a chiplet part, which means now the handling guys now ready to go. But the below 55, I'm not sure they are ready for that. But I believe they are actively developing some technology can deal with the below 55, maybe above 10 micrometer sort of handling capability, as well as inspection, as well as the testing. So yeah, I believe a lot of activity going on the supplier or equipment vendors.
So
Okay.
yes, Andreas, I mean, if I could jump in on that, I think you know, as these structures get more and more complex and they move from planar to 2.5 or 3D or more type structures, and the interconnect pitches get finer, it becomes harder and harder to look at what's happening between those layers, right? Traditionally, as Max said, you have a planar system, you can do optical inspection, AOI, you do that for system boards as well. But as you start to move to these 3D structures, you need other tools to be able to see through the structure and to see what's actually hidden inside the building, to use Max's analogy. And as those pitches get smaller and those interconnect distances, the gaps between the dies get smaller to eventually being non-existent when you're doing hybrid bonding, that becomes a challenge. I think the other discussion to have is, you know, is it about inspection or is it about metrology? Because as we mentioned earlier, rework is pretty difficult. So doing inspection, all you're going to do is find the defect, which quite frankly, you should be able to find in many cases at final test as well. So I think what you really need to do is find the metrology tools to be able to monitor the process and see what's actually happening. You know, are you getting delamination between the layers in case of hybrid bonding? Is there particle issues in there? Are there surface contamination issues that are causing some level of variability in your process? And so we are definitely going to need advanced tools. And like I said, whether they're inspection or metrology, we have to find a way to be able to look through some of these three-dimensional stacks. So whether that's X-ray, acoustic, other types of techniques, I think the industry is already addressing that and needs to continue to address it.
Yeah, I think that's a really important point, Elko. Like the differentiation between process characterization tools and establishing process predictability, as opposed to finding outliers and the test faults, is that distinction, I think, is quite important. Because if we don't get to the point of process predictability and process control, then that could be another obstacle here. But you know, if you think about the geometries that Max is talking about, I mean, fundamentally getting down to 10 micron pads, you've got completely new set of issues in a 3D environment where SSO and other type of defects that you can only catch at the system level, or you can know through process control and process design are in control. Otherwise, you're into very extensive and expensive system level testing, which, you know, the number of nodes in these designs is very extensive.
Yeah, I would also think that, you know, as you move to these tighter and tighter pitches, and of course your I/O counts, the interconnect counts are increasing. You're going from thousands to tens of thousands to even hundreds of thousands. You know, I think these tools are going to need some advanced analytical capability, and things like AI and other vision systems or other types of process monitoring systems are going to be required, because it's going to be very difficult to just analyze a couple of pieces of data. You've really got to look at a lot of input variables and be able to detect that drift before it becomes a defect. Because you're dealing with a lot of expensive pieces of silicon here. So if there's any drift, you want to be able to calibrate the process back to center before it moves out of control.
Yeah, I agree.
We got another interesting question here from the audience. shipping these in a wafer form, meaning the chiplets, with wafer maps exposed, yields, will expose the yield levels, which the chiplet supplier may not appreciate. And alternatively, shipping these in intermediate packaging like tape or reel or waffle pack will create an economic tax. And so, what's the answer here from a raw cost perspective and from a exposure perspective? Will the new product be a wafer instead of individual chiplets, for example?
Yeah, I think I'm not sure what the answer is, Andreas. But I'll also comment that there's other factors to consider as well, like ESD, and when you're thinking about handling and packaging. So it's just to add another variable to the equation there.
Yeah.
Yeah, I think it's that will be an interesting dynamic, and I think the question will be the ideal format certainly for a packager is going to be for chiplets to come in wafer form with wafer maps, so that we have the ability to adjust the die thickness as needed for a particular application. But certainly things, waffle packs are not an alternative, but tape and reel could be an alternative, certainly for smaller die chiplets. Those can be fed into flip chip bonders using chip shooters and other ways, which actually has some potential economic advantages over more traditional techniques. I think it's ultimately going to come down to, if the company that's doing the device integration, that's specifying the chiplets, negotiates a chiplet price, then from a material flow perspective, it's coming to the contract manufacturer. And so there may need to be some agreements implemented where the yield information stays contained within the manufacturer because the chiplets are being consigned. So that's one option. And then to Max's point, if you're following the cube methodology, then that integration may be happening before it ever reaches the assembly house.
Yeah, another point is the existing infrastructure and the scalability. The model today is we have incoming wafers or the tape and reel, for different, smaller form factors. So to leverage that and to scale that, the wafer form of the die packaging, if that's the technology that's been picked as a plan of record, that's highly recommended.
I mean, the third option or another option that's available is, something that's been done in the CMOS imager space for a while, where the die suppliers ship in reconstituted wafers of all known good die. That adds some economic tax because it's another operation. And it removes a level of flexibility for the assemblers because we can't do any post-processing on those devices at the wafer level, such as bumping, thinning, RDL, etc. But that's potentially another option, and it's used, like I said, with CMOS imagers. We see it done with some power devices, etc.
Andres, we have time for one more question, and then
Okay. So I think I'm gonna reserve the last question for me, right? Because for all the panels, like do a little survey for the panelists. How many chiplets could you see integrating into one package by 2025?
That's a tough question. It comes down to the number of dies, the die size, the design. We can focus on the die to die space, how to reduce it now. About 150 microns is what, between 100 and 200 microns. So it comes down to, the number of dies comes down to the design. Typically the way we work in our model is, throw all the stuff to us and we'll try to figure out the best way, to to accommodate it. And of course, there's the cost and the size, the form factor, the X, Y, and Z is going to modulate. So I think it's very subjective to pick a number as to the number of dice. But we can focus on the maximum packet size that we can look at, and something that we have looked at is up to 100 by 100 millimeter, potentially a package that could use our existing infrastructure, because there's still some investments that would be needed, but that's how I would address that.
Yeah, so I think the way I'd address it is I agree with some of the things that Swami said. There's the physical limitations. I think from a mechanical assembly perspective, we are actually in production today with 15 to 20 chiplet package integrations. But generally what you're talking about is, a core device with 10, 15 or more of one or two other devices. So that's easily manageable today. If we're talking about 20 different chiplets, that requires a tool set that may not be available yet today in terms of the number of inputs, with the exception of if you were using a chip shooter. So in that case, the chiplets would absolutely need to come in and tape and reel for us to handle that many different chiplets in a single package. But I think ultimately it's going to be more gated by the economic challenges of the yield stacking and what is the resulting yield going to be when you get to that final product at the end of the line. I mean, I like I said, from just a physical capability to integrate, by 2025, you could easily envision doing 25, 30, 40 chiplets, but is that going to be economically viable? And is the supply chain going to be ready to deliver in the right formats? I think that's the bigger question.
Okay, all right.
Andreas, I might offer that, I think everything Elko and Swami said was accurate. This is an immensely complex problem in terms of the economics, and I guess the answer to all of these complex questions in the universe is 42. So that's going to be my answer.
All right, we'll go with that.
All right, I think they're kicking us out to a coffee break now. So thank you, all the panelists. And
thank you.
We will come back at 10:55, at 10:54 precisely. So we will have our final session, and we'll start with David Greenfield talk from Intel, and then we'll do a panel on end user as well as from system integrator. Thanks, everyone.
Thanks.
I'm making hot water and a sandwich.
Oh, come down.
DJ, are you there? Or Michael?
Hey, David. Yes, I'm on.
Where's my share screen button?
Hey, David. Yeah, I'll hand that to you in about 10, 15 minutes.
Okay, I was worried that it disappeared on me.
No worries.
All right, I'll come back then. Thanks.
So we are right at that time. I would like to welcome David Greenfield from Intel, and they will provide his perspective, and then we'll go into a panel from system integrator and end user. Welcome, David. David, we can't hear you if you are saying something.
All right, can you hear me now?
Yes, perfect.
Excellent. Good morning. This is the Deliver/Business panel. We've assembled a fantastic group of panelists here. We're going to start with a dry and boring keynote presentation, which will be followed by much more interesting updates from our system integrator and end user experts. All right, so that dry and boring keynote presenter is me. And I'll talk about a set of challenges we've seen in Intel at looking at this ecosystem of potential providers of chiplets. So I'll start by looking at what the opportunity is. I'll scope out that opportunity and present a case study on some of the key challenges and learning that we've identified and gone through through our experiences. Several of the discussers today have already highlighted this point, that it's absolutely essential that we identify a compelling problem or reason to use chiplet technology. And if that compelling technology or reason doesn't exist, then keep using something discrete or keep using something easier. One example of that technology is in the wireless radio space. And high-speed data converters are going to be needed for the evolving standards, 5G and everything past 5G. And the challenge here is that the number of data converters is likely going to be in excess of 50. And if you want to take a data converter and attach it to an FPGA, a processor, or something else, and it's a high-speed data converter, you've got to use a high-speed interface. Today, that chip-to-chip high-speed interface is JESD, and it today uses about 2 watts per channel. It'll be moving to about 1 watt per channel. But if you've got over 50 channels you've got to integrate in, you're talking between 50 and 100 watts here. And if the total budget is at 75 watts for reasons of you've got to ensure that there's no active cooling within a system, that's going to be a problematic issue. So in this area or this example, there was simply no other alternative but to look for a die-to-die interconnect that would facilitate the use of getting the power down. That is something I would view as compelling. At Intel, we've got a lot of experience in disaggregated design. We worked with DARPA CHIPS program that was mentioned earlier as identifying a proof of concept and partnering with an external supplier, and so have experience in that space today. We've also announced a release of an FPGA technology that will be used in future products with analog capability tied to FPGAs. The Programmable Solutions Group, which is the Altera group at Intel, has been using disaggregation for a number of years. And an example of where this is useful is we've got an FPGA fabric die surrounded by transceiver dies. And this allows us to bring out different transceiver technology at different times. So we could have a transceiver that supports 20 gigabit per second or 40 gig or 112 gigabit per second. New emergent standards like PCI Express Gen 4 moving to Gen 5, or even having a tile that supports something like UPI or CXL. So it gives us the opportunity to mix and match different technologies in a more price competitive manner. We've also introduced something, a GPU technology we've called Ponte Vecchio, which uses a large number of die. That is an internally developed product where everything inside it is Intel based. So there's a mix and match of experience of using both an internal ecosystem and external ecosystems of chiplets coming from different suppliers. So in terms of the business case for a multi-chip package, I think there's a number of questions that need to be answered in terms of why you would do this. And identifying that business case is, the first step is, what's the cost to productize the MCP? And our experience is that this is not a 6-digit cost. It's likely in the millions of dollars. And so you've got to ask yourself, who's doing the work? How extensive is the validation work? How many units are going to be needed for volume validation? And then the next question is, if we're putting together a system of chiplets, do the chiplets exist? Are they off the shelf? Versus, is there a need to find a development partner to help put together the chiplet that's going to be integrated? And there's a completely different set of challenges that are going to be important to resolve if the second party needs to develop the new chiplet. And I think it's important to ask yourself, why bring in a development partner? There are a large number of challenges and extra complexities that come in when you bring in a second partner, and there better be a compelling reason to do that as well. So once you've got a fair scoping of what the investment is that's required here, then you look at what the market opportunity.
David, we lost your audio. David, we can't hear you.
I'm gonna drop David a quick message in the chat. It looks like his audio is disconnected. Ravi, in the interest of time, while we wait for David's audio to reconnect, should we move on to one of these systems integrators?
There's obviously a much higher cost, but even for productization, as I'm highlighting, this is a significant cost effort. Certainly less expensive than developing a chip completely, but it still is a material cost that's involved here. So the deal that we put together on the specific case study had a number of key parameters. There was an NRE to accelerate product development. It was a KG deal, known good die deal, with escrow provisions. That we defined the IP ownership and license rights. There were some exclusivity terms that we had to think through in terms of what type of parameters we wanted to include. And then we looked at KGD. And I think and a few people have talked about this already today, but there's a very important question that needed to be asked, which is, what if the KGD is actually UUD? And for those of you wondering, this is of course an acronym that I just made up, but what if it's unknown ungood die? How do you handle that? And in the case of an FPGA type design, where you can have a very expensive FPGA tile or chiplet that could be surrounded by some less expensive chiplets, if the less expensive chiplet is the potentially unknown ungood die, and you have to toss the entire package and you don't find it until you've built the product, there are some significant cost considerations that need to be thought through. Then there were a few extra things we learned along the way. And again, first time we went through this, we needed a large number of test units and a large number of die here. So who pays for that and at what price? And questions on who owns the IP rights to the packaging between the chiplets. So it's pretty obvious who would own the chiplets themselves, but what about the interconnect technology and the packaging design? And then how much uncertainty on technical issues can we live with, or could anyone live with in going through this? So these were some of the things we had to work through and learn as we went along the way. And so the summary for us and advice that I would provide here is, find a pathfinding opportunity for business model and KGD exploration. And what we found is it's a lot easier to deal with revenue sharing challenges in a market where there's ample margin than to look at trying to figure out how to share margin in a very cost-sensitive market. And finally, make sure you identify a compelling technology solution. And these might be areas like size, weight, power, cost, yield, but just trying to find something to save area probably is not going to be a sufficient reason to deal with chiplet integration, because there's a number of challenges that have already been discussed today. So with that, I'm going to introduce our panelists, and the first person that will be presenting is Anu from Microchip, and I'll turn it over to you.
Thank you, David. Can you hear me and see my webcam?
Can hear you well, yes, thanks.
Okay. I want to just thank the organizers for allowing me to present on this panel. I'm Anu from Microchip. Next slide, please, David. So the key driver to moving towards chiplets has always been lower cost. And how do we achieve this? Click, please, David. I think if you, yeah, okay. It's been cost reduction, and this has been touched upon by both Javi and Gary earlier. How we do this is we use existing silicon. So if you've got silicon proven IP sitting on the shelf, you reuse that, and therefore you reduce your R&D cost. It also enables you to create more product faster, so a quicker turnaround time, marketing multiple SKUs. So all in all, it looks like a winner. Another click, David. The next piece is the innovation. So when you don't have to go soup to nuts in 3 nanometer or 5 nanometer, and you have the ability to innovate at different process nodes, you can go much faster. You also don't waste money and time. For example, why would you redesign a PCI Gen 3 macro in 6 nanometer when you've got a perfectly good one in 28 nanometer, which meets the spec? So doing that enables you to create smaller die, especially on the cutting edge nodes. It improves yield, smaller die, and therefore now you've reduced your operation costs. So given both the R&D cost reduction as well as the operation cost reduction, it looks like a winner. So far, the business of chiplet integration has highly been vertical, and this has been demonstrated really nicely by AMD, by Intel, by Marvell. Here at Microchip, we've got a large portfolio of IP, and we've got everything ranging from 300 nanometers to 6 nanometers. So in theory, for a complete solution, we could go with vertical integration. But really the question is, how do we add third-party IP, third-party chiplets into this and make it a viable ecosystem? Next click, please, David. And I see the key to that, or we see the key to that as standardization. I know that Giri earlier today mentioned that standardization stymies innovation, and to a certain extent that's true. But I do believe, for example, the few pieces that I'm talking about are die-to-die interface. And it's been mentioned before, I think Tony brought it up too. There's the serial and there's the parallel. And within each, there are a couple of flavors. So within the parallel, there's 3 or 4 different types. But for a chiplet vendor to be successful, to be able to sell his or her chiplets in volume, they need to hone in on a minimum set of interfaces, knowing that they wouldn't have to create a chiplet in 5 different die-to-die interfaces and have small volumes of each, because that's not a good business solution at all. The second piece is for system integrators to be able to second source, third source, or have flexibility between vendors. There needs to be standardized pin templates, so you can actually swap out a chiplet should the need arise. Next click, please, David. And now on the operation side, so the KGDs come up multiple times today, and I know there's no clean answer here, but it would be nice to have standardized KGD tests. So in a vertical integration, this becomes a lot easier, right? You're integrating your own chiplets. It's more of an ad hoc methodology, and you follow the same methodology within your organization. So you have a better chance of success in knowing what you get. But when you have third-party KGD, is there an agreed upon standard for it? And there's a whole lot of acronyms that came up today. I like the one that David just brought up. I think he said the U, unknown good die, and then there's the maybe good die and almost good die. What is the standard? How do we know? How, as a system integrator, do I have the confidence that the die coming in is indeed good die? On a similar vein, when you look at security protocol, so within a vertical integration, you have a certain security protocol injected into your chips, maybe a die probe, to ensure that you are getting what you think you're getting. In a third-party environment where your supply chain for third party is different, it goes to an OSAT, it goes to an assembly. How do you know you're getting the die that you thought you were getting? So are there standardized security protocols? And of course, a solid supply chain. If I'm expecting to get 50 wafers from vendor, chiplet vendor A, and I get 45, how am I supposed to fill that gap? So there's got to be a solid supply chain that assures me that I'm going to get the request that I put in. Next click, please, David. And so if we allow for this kind of consistency, and we allow for this some amount of flexibility for multi-vendor possibilities, I think we can build a better business system. I agree it has a few drawbacks here and there, but this would build confidence for system integrators too, that they can actually integrate third-party chiplets and still be successful, as well as for chiplet vendors to know that this is actually a good ROI for them, as opposed to serving multiple markets with small volumes and not being a good business deal. So those are pretty much our thoughts on the chiplet business ecosystem. Thank you. Back to you, David.
Thanks, Ramin, over to you.
Thank you. I sent you latest stuff because I wasn't sure if you are sharing my slide or yours.
I am sharing what I think is your latest.
Okay, so I cannot share my own slide, so you can go through that. That's fine. I can go through this. This had some issues, but I can walk through that. Okay. Good morning, everyone. This is Ramin Farjad. I'm in charge of networking automotive PHY development at Marvell. So today I'm going to cover the chiplets and the delivery of the chiplets in this new ecosystem that we're talking about. So as you know, the idea of chiplets has been used for two main purposes. One has been using it for large SoC disaggregation, mainly partitioning a large die into smaller chiplets to reduce the development cost and also time to market. So every time we want to move from, let's say, 16 nanometer to 7 or 5 nanometer, we don't have to port all the IPs, especially, let's say, analog IPs and so forth, to this new process. And of course, once we do that, we can also develop the specific IPs. There is RF, ADCs, analog, and so forth in their special process that is optimal for them. The other use case that we have is building system in package, or SIPs. And the main goal for that is by shrinking the system into a system of chiplets. By removing the packages and being able to put them closer together, we can create better interfaces between them, higher bandwidth, lower power, and so forth. That results in higher performance of the final system. It brings us a smaller footprint. That means even low cost, especially for phones and so forth. There are other advantages too. And the low power is a key part of this. So the main focus here, of course, moving forward, we know that trying to have an ecosystem for a large SoC and building into smaller IPs will take a longer time. That will be the next phase. The upcoming phase that we see is building the systems into a system in package using chiplets and using off-the-shelf chiplets for that purpose. So next slide, please. So in my opinion, building chip systems with chips or chiplets are not fundamentally that different. What are chips? Chips are pretty much a piece of silicon, like a chiplet, that is packaged and then all placed on a, let's say, PCB board and then connected together. So the process for that, as you see on the right side or left side, for a conventional system, they receive this good chips that are screened at production test, and then place them on a package on a PCB, and then connect them together through these standard interfaces. Could be PCIe, DDR bus, and so forth. That's the physical layer. That's kind of like an agreed upon that for this application we use PCIe, for the other application connection to memory we use DDR, and then a specific protocol that industry has defined as a standard. And then we finally test the final system. On the other side, on the system in package, we have to have the known good dies that my industry colleagues already talked about. That instead of having a known good package chip, we have this known good die that is done at the wafer level test. And then we put all these KGDs on a package substrate and then connect them again together. And all we need is this interoperable standard interfaces. Could be XSR, BO, HBM, and their associated, let's say, MAC layer or control layer. Again, fundamentally, there's no difference between building a system with chips or chiplets when we're talking about SIP. And all we are doing is shrinking a system into a smaller footprint at the end of the day. And then finally, we have to test this system and package. So of course, there are differences that I'm going to kind of touch on in the next few slides. If we can go to the next slide. So first of all, routability of the interfaces is key. So of course, if you want to go buy a bunch of chiplets off the shelves and then connect them together, these chiplets are not perfectly designed that in all possible permutations, they match perfectly together and they can abut and side by side. We cannot have basically one size fit all chiplets and build this perfect case that you see on the side in this picture, that everything are nicely connected together. Of course, in special cases that, simple cases, you can have build an ASIC, which its ports, let's say, connecting to HBM is very clearly defined, and then put these HBMs right next to the ASIC. But that's not something that can be applied in a general sense. If you go to the next slide. David, thank you. So the key here is to have proper routability, meaning these chiplet interfaces should have or be able to drive a certain reach, that once we place them on a package substrate, we can easily connect them together without having to worry that they have to perfectly match with each other. So based on the experience that we've seen and from the system vendors, especially on the SIP side, something at the minimum about 1 inch is good enough to enable such systems. So again, routability of these interfaces is super important, and that's something that you usually do not get, do not get an interposer type of interface, because interposer reach is limited. But on a PCB or organic substrate, there are interfaces such as BO, such as XSR, and so forth that can provide that distance. Is really key to enable this ecosystem of buying chiplets off the shelf and then connecting together to build a new system. So next slide. The other key issue, as everybody touched on, is having this known good die. On top, you see this traditional system that, or the process that we have the IC design, wafer manufacturing, then we probe the wafers, find the known good dies, we package them, again test them.
Final minute to wrap it up, please.
As part of the production test, then we test the system and so. In a chiplet case, we don't have the package. We cannot test the package part. So we have to have a known good die and then jump to the system test. So it's very critical that at wafer level, we get a very high screening ratio or screening yield. So next slide. So in summary, as I shared, chiplets can potentially be marketed and sold like traditional chips. There shouldn't be fundamentally any difference. but we have to have certain things in mind, that standardization of the interfaces is very important. The routability of these interfaces are also super important, and most of all, having a great wafer level screening with very low defect density or identifying is super important, which is of course very difficult to do in the case of micro pumps. And of course, the other question is supporting it. Who's going to support the final system? So pretty much just like a typical systems, like Cisco sells a box to a customer, Cisco would be responsible in front of the customer to deliver a good system. There can be problems with the chips inside, but that system vendor will directly deal with the chip vendors, or in this case, chiplet vendors, to resolve the issues. But the final system vendor would be the responsible party there. Thank you.
All right, great, thanks. And with that, I'll turn it over to the end user session.
Thank you, David. Yeah, just go back a slide, actually, please.
Sorry.
Okay, yeah, hi there. I'm Ben. I'm here to represent the ODSA end user working group, composed of the companies you see there: Alibaba, Facebook, Google, and Microsoft. Yes, thank you, David. Next slide. Yeah, just a quick disclaimer. Yeah, the slide deck here and everything I was going to say kind of represents our collective view across all of the members I just mentioned there. Doesn't really represent any one position of any one of us. Thank you. Okay, next slide. So I guess one of the advantages of having the last presentation is everything I was going to talk about has kind of been covered. So, but yeah, I think we can give it a slightly different angle. And so this is the end user view of enabling a chiplet marketplace. The sort of need for the chiplets that we see, the kind of gaps and gives across these areas, the business and commercial on the technical side and the software management side, and then the opportunity as we see it from the end user side. Thank you. Next slide. Okay, so yeah, it's been discussed a lot. There's certainly a real need for a chiplet business. In particular, we see that a lot of the critical system IPs are not really scaling as the technology nodes decrease. Particularly, there's a couple of reasons for this. Really, one of them is just sort of physics. Some of the IPs need to drive kind of 50 ohm loads, and sort of that dictates the size of some of the transistors. And then another aspect of it is the actual physical size, and we see that bump pitches, either C4 bumps or micro bumps, have kind of pretty much flattened out, and so the IPs themselves are becoming pretty much bump limited, and so even porting the IPs to those new technologies doesn't necessarily gain us any real area or sometimes even power advantages. And again, sort of building very large monolithic die really does yield very badly, and that has a knock-on effect on the supply chain as well. In that, if you have a poorly yielding die, then you're going to launch more wafers, and those extra wafers take fab capacity and of course have a knock-on effect. Obviously, the fab cycle times are longer as well, and so the ability to port IPs to the new technologies just takes longer, and that, as I said, kind of limits how quickly we can adopt a new technology. The fabs are qualifying the technologies for SRAM and logic, and so that's the technology we'd like to take advantage of. And if we could get held back because a critical IP that we need hasn't yet been ported onto that technology. And of course, we get a faster time to market because we can leverage known chiplets, which means we don't have to spend time developing that particular part of the system, and we can pick up essentially working components and focus on the areas that we'd like to focus on. So yeah, we can definitely see there's a clear need to enable a chiplet market ecosystem. Okay, next slide. Thank you. Okay, so looking at the business and commercial side, we identified some gaps and some gives. Certainly on the gap side, we would definitely need to see these chiplet die available from greater than one supplier. and really just as we see in the industry at the moment, sort of supply chain issues really can hurt the whole industry. And so certainly some ability to guarantee supply of chiplet die is pretty much essential. And I guess coupled with that as well, sort of pushing volume through the OSATs is also a challenge, particularly in these times of sort of high demand. And so again, we could see that the OSATs would need to sort of invest in extra capacity, and also I guess inventory management as well, where you have chiplets arriving from lots of different sources that all need to come together to create the final product. And overall, just a general innovation in the whole business model as well, and how everybody works together across the different suppliers. But yeah, on the gives, I guess the industry knows how to do known good die. There's certainly a great range of IP availability across many different nodes. And what maybe a solution to help with the supply chain is that the electronics industry has a great set of distribution channels already, sort of to support the sort of PCB market. And maybe they could also act as a buffer for kind of chiplet sort of product as well. Okay, next slide then, please. Okay, yeah, on the technical side, I think it's been talked about a lot. I guess a real lack of sort of a crisp, solid specification as to exactly what these chiplets are going to look like. And so I think the real enabler we see would be to create a proper open chiplet specification, kind of like the OCP specs that exist today, which would list out speeds and feeds, sort of footprints, mechanicals, die-to-die interfaces, general datasheet parameters like power envelopes, and of course the obvious design collateral to enable us to design in with the chiplets. And I think another aspect that maybe hasn't quite been touched on is also, I guess, proving interoperability. If we are going to be sourcing these die from multiple suppliers, then we would certainly like to be able to see that they are like-for-like compatible and interoperable. Thank you. Next slide. And then another aspect that hasn't really been talked about quite so much is I guess just managing and bringing up a system that's comprised of a lot of different chiplets. Maybe something Anu said was sort of how do you discover the chiplets that are in your system and obviously do that in a secure way so that you know that the chiplets that are deployed are the chiplets that you're expecting. Another big factor is obtaining telemetry data from these chiplets because they are typically deployed in large volume, and just monitoring the health of that system is very important. And also just coordinating at a package level the various resources that are available. If you look at a PCI Express kind of specification, it really focuses on boards and removable boards. And so I guess taking that and miniaturizing it down to the package level. On the give side, certainly a mechanism to achieve this management by a simple out-of-band sort of hardware interface, and then really building on top of some existing open source management interfaces and protocols. There are quite a few out there that we could utilize in order to expose a common sort of API to manage the chiplets. And then talking about an API, I guess also facilitating an extensible API such that people can add value to the chiplets and expose the particular aspects of a chiplet. And so yeah, again, we see all of that taken care of with a sort of open chiplet specification developed, I guess, by the ODSA. Okay, thank you. Next slide. And then I guess we had a look at some potential chiplet applications. I think has been talked about a lot. PCI Express looks like a very good fit in terms of sort of offering that initial kind of maybe breakthrough to kickstart the chiplet ecosystem, and then extending that into many other different high-speed interfaces, the obvious LAN and WAN kind of physical layers. And then another aspect that David mentioned on maybe a good opportunity as we transition to 5G and the Open RAN systems. And then I also sort of enabling proprietary inter and inter-rack kind of communications that is typical for the end users. And then what's nice about the chiplets then is it gives us this ability to modularize the SKUs, the different products that we're building, and I guess also maybe move with the times and sort of upgrade as we go without necessarily have to change the entire product. And then we also potentially enable some more advanced interconnect solutions as well, some of which were sort of touched on earlier as well. Okay, so next slide then, please, David. So I guess just summarising then, you know, we think that the chiplet opportunity here is really very large. There's a lot of new revenue and new opportunities, new techniques to really drive and enable this chiplet ecosystem. I think everybody understands that the gives are well understood. There's a very good sort of prior art example through HBM that kind of shows that, that delivering chiplets, as we said, if it's a chiplet or a kind of a memory module, but the sort of practice is understood, and managing the integration of those. And then, so I think the chiplet opportunity really just takes that concept and expands it. And then really, yeah, a lot of the gaps are solvable. The ODSA is working on all the pieces that we need to really enable an open chiplet specification. And so what we see is collecting up all these pieces that are in flight within the ODSA, the die-to-die PHYs, the adapter layers, the software management protocols, and really bringing it all together. And you know, we see that the ecosystem momentum is really building, and you know, we think there's a great opportunity here to give it a push and get the ball rolling and really start to enable this this marketplace. Thank you.
All right, thanks.
Last slide. Thank you, David.
Can we turn off sharing here? All right, so we're going to start the Q&A session now, and I'm going to kick things off with a couple of questions for the panelists. So the first question is for Ben. How do you see addressing niche markets for relatively low volume, which are supposed to be enabled with this chiplet approach?
Okay, yeah. Thank you, David. Yeah, so I think sort of addressing the niches is maybe the opposite of what we want to enable with the ecosystem. You know, I think the ecosystem works best if we create chiplets with very broad appeal. And I think that's really the challenge to the chiplet suppliers is to think about what the end users need and create chiplet products that satisfy the wider market, because that's really going to enable the volume and the sort of reusability across all of the end users.
All right, thanks. Wafer, do you want to add anything?
Yeah, I think the specialized segment of market does impose a challenge here, because for a dedicated, you know, for this type of a general market, so if we want to make a dedicated chip, probably not worth the effort, especially with a low risk of, low ROIs. But on the other hand, if we use like a general purpose solution, and we may have, you know, workable solution, but probably with, let's say, low performance. So by putting together the chiplets with the desired functionality and also proven working solution, so this will make the, you know, like a heterogeneous computing so we can provide quick yet effective solution to serve this purpose. So I think chiplets-based approach sounds like a cost-effective solution to address this market. Back to you, Dave.
All right, thanks. Nicholas, do you want to add anything here?
Yeah, no, thank you, Ben and Weifeng there. I think you guys have hit the nail on the head. The first thing which I wanted to say is actually what Ben had said at the beginning exactly, which is to enable the niches, we need to first enable the larger use cases. You know, I can't attach a niche chiplet to another chip which doesn't already have the ability to work in this way. So that's the first point. But once we get to there, there's two key areas, I think, from our side where we would want to go to make sure that we were able to use chiplets in niche environments. And the important thing is these niches do exist in our data center. That's the first thing to say. But we need to have a low friction workflow to be able to enable them. And that involves basically system level integration. How do we integrate with existing components? The physical layer, the link layer, and something Ben touched on earlier, actually the monitoring and the system configuration. If I can't go to my production engineers with a good story in terms of how that's going to work, then it's not going to get off the ground. And the second one is the workflow standardization. Where do I go? Whose neck do I grab if something doesn't work? These are the things that we need to be able to address. Otherwise, niche markets will not be enabled.
Great, thanks for the answers. Next question, and this is for Ramin. How do you see the division of the test and validation of the final system and package products between the deliver phase and the build phase when these are not vertically integrated?
Sure. As I also shared in my presentation, I think at the end of the day, the system vendor would be the party that would be responsible for the quality of the product that is delivered. But then at the end, the chiplet vendor, so that they receive meets a certain criteria of defect density or yields. And if that target is not met, eventually the system vendor and the chiplet vendor have to work with each other to find you that. So I don't see a big difference fundamentally versus the chip vendors versus chiplet vendors. The main issue is how to get that target yield high enough at the wafer level screening that once these chiplets are put together in a system in a package, that usually there are expensive SOCs at the end of the day, or SIPs, I should say. We do not have high, dropouts.
All right, thanks. Anu, do you want to add something there?
My answer is very similar to what Ramin said. The first, at a very high level, is basically the first step is you get known good die from your chiplet vendor, right? Now, if there can be standards where the yield is good and everybody wins in that game, that's perfect. The second step is the system integrator essentially now tests for the interconnect between the chiplets. And that could be through BIST or functional logic. And what they're looking for is, were there any defects during assembly when putting all of these chiplets together? And that's system level testing. And then it goes to the field. Now, if there is an RMA on the field, what happens? Well, it comes back to the system integrator who then tries to isolate to which chiplet caused the problem, and then RMAs it back to the chiplet vendor. So I believe that would be sort of the cycle we would follow. Back to you, David.
Okay, Weifeng, did you want to add anything on that last question?
Yeah, I just want to say for this, validation and testing issues, actually for any modularized design, either software or hardware, so always has the, this kind of issue at the whole system level. So I think it's critical to have, let's say, unified access to all the modules. This has to be addressed across the chiplet ecosystem, because at the same time, we also need to address the, similar usability issues at the software level, including, let's say, profiling, debugging, runtime management, and interoperabilities between the chiplets. I think some panelists already mentioned this in the previous talks. So at the end of the day, because it's the end user who has the word to, decide how easy we can take advantage of the chiplet functionality and the efficiency. So I would say the user-friendly and the unified access for the ecosystem is very important here, because at the end of the day, it's really the usability is the key. Back to you, Dave.
All right, thanks. Next question is for Ishwar. What roadblocks or gaps will the end user see either today or tomorrow for chiplet-based open ecosystem?
Yeah, actually listening to everyone today, I didn't even know so many roadblocks existed, but I appreciate it. So yeah, I think we've spoken a ton about the roadblocks, right? From the known good die, the software ecosystem, the standardization of IPs, workflows, multi-sourcing vendors, all of it, right? The whole problem right now is that this ecosystem is nascent from a data center adoptability point of view. We need to get it mature. We're on the right track. We're doing all the right things. We need to accelerate it. All of those are things that we need to go address. In my opinion, honestly, we need to get some proof of concept products out there. The quickest path to doing that is going back to what Ben was saying. We need to take a couple of examples of things where the upper layers are fairly stable. PCIe, right? Take high-speed SerDes, right? Things where the upper layers are pretty standard, pretty stable. Use chiplets to go demonstrate how to make those things work. And once we have those proof of concept products out there, a lot of the issues that we've talked about today can be ironed out by the industry as a whole. That's my opinion on this. Oh, back to you.
All right. Anu, do you want to add anything?
Yeah, so two things here. One is foundries need to allow for known good die to be shipped to a third party for integration. And I've seen that where the foundries like to have the whole enchilada, so they want to do everything from start to finish and not necessarily ship their die, known good die, to a third party. And that's a roadblock for heterogeneous integration. The whole idea is to be able to have multiple foundries be able to ship their parts to a vendor. The other small piece I want to address is, and I don't know if you'd call this a niche market, but assembly for smaller volume manufacturing, and I'm specifically referring to the aerospace and defense industry. Their volumes are to the tune of 100,000. So even if I got a ton of money from NASA to go and assemble a bunch of chiplets together in the form of heterogeneous integration, I couldn't find an assembly house to do it because the volume is at 100,000. So there's got to be some enablement for smaller volume. The technology exists today for multiple people to do it, but it just needs to be enabled. Back to you,
Great.
Dave.
Thanks, Anu. Nicholas, do you have anything further to add there?
So I mean, Ishwar and Anu covered a bunch of the key points I think I had on the sort of supply chain side and how to enable this stuff, which I think is one of the big questions. The only other thing I would probably add to this is more sort of on the technical side, is looking at the protocol layer. I know Tony mentioned this earlier today, and I think Bapi has been saying this since about 2019, if I remember correctly. But we need to really look at how we integrate the protocol layer. Now, I know there's work going on like the pipe adapter, which is a fantastic first step, and PCIe makes perfect sense as a first target for something like BOW. But there are some use cases we see internally where we might want to have a very lightweight standardized link layer protocol. And kind of looking around, I haven't really seen anything which really maps to that. And so maybe us spending a bit of time thinking about that at some point in the near future would be actually something which from our side would be very interesting.
All right, great, thanks. Another question, this one's for Ramin. Are there new services that are going to be needed to deliver solutions to the customers?
New services, I would say the OSAT part is an important step of putting these chiplets together. And these are special services that, which is somewhat different from the traditional way that things were being done, especially with using interposers as a way of integrating them or other more advanced wafer level packaging. So these are all the new type of services that groups like ASC or Amcor, they need to start providing, and in a wider scale, as Anu mentioned earlier, especially in certain things are at low volume. It may be difficult to get them, especially in these high-end technologies, I would say, with micropumps and so forth. So those are the kind of services that needs to start growing to be able to provide the necessity for integration of SIPs.
Great, thanks. Ishwar, do you want to add anything?
Sure. In my opinion, one of the things that at least I haven't seen, or maybe I missed it, is when we talk about standard protocols that exist on, say, the PCB, like PCIe, a lot of those have things like a compliance test, right? Where you can actually have a suite of compliance tests to make sure that you have interoperability, you have known good die, you have a whole bunch of these things, the problems that we've been talking about today. As part of the solutions that gets delivered to the customer, I would expect at some point, for certain classes of chiplets that we develop, we'll bring them into classes, and for certain classes, we'll come up with a compliance suite of tests that people can run against, and as end users, we can actually verify that those compliances have been met. And I would like to see that being one of the solutions in the space.
All right, thanks. And Ben, anything further to add?
Yeah, thanks, Ishmael. Yeah, I touched briefly on that as well in my slides, that maybe some kind of reference sort of substrates or sort of ability to package the chiplets and test them against each other would be a great enabler. But I think the chiplet suppliers maybe need to consider the complete sort of end-to-end experience of the people using the chiplets, and also right back to the IP providers as well. If you think of an IP provider maybe providing some IP that goes into a chiplet, I guess traditionally IP providers work directly with their end customers if you happen to license an IP. But now there are multiple steps in the path, and so an IP provider might be providing their IP to a chiplet provider, and the chiplet could go out into the ecosystem, and that IP provider could suddenly have 10 or 20 customers that maybe all need support and all need some particular help or sort of debug services. So I think there's certainly assistance there, or at least some new thinking in terms of how to support the ecosystem as a whole. And it's not, it's definitely going to get broader. And you might not even know who your final end customers are. So yeah, I think, and then I think, like I said, the industry just really needs to implement sort of an entire sort of new process to kind of handle the chiplet products through the system. It kind of goes right back to what Alan said very earlier on about kind of the TTL chip model that some of us grew up with. The TTL chips could be bought from 4 or 5 different suppliers, Fairchild, Natsumi, TI, and you sort of plugged all those together onto breadboard or wire wrap. That's what I'm showing my head. And those chips just work together. And I think the chiplets is the 25-year sort of evolution of that TTL standard that was put in place a long time ago. It works for PCBs, and I think it's we're getting it to work on a chiplet level.
Of course, one thing I can add further is that, especially for OSAT.
Next question is for either Anu or Ramin. My experience at a large supplier in our part.
Yes, we lost the.
I'm sorry, can you hear me?
We hear you. I guess you don't hear us.
Can you hear me?
Yes.
Okay. So let me try again. Question for Ramin and Anu. My experience at a large company is that we're happy for our partners and our customers to pick any die-to-die interconnect they want, as long as it's our die-to-die interconnect of choice. So when you're looking at putting a die-to-die interconnect on your chiplets, which one are you going to pick?
Basically, the question is there are a number of available die-to-die, maybe XSR, Bow, and so forth, and how do we go about picking them? Is that the question?
Yes.
Anu, you want to go first, and I follow.
Yeah, so this is something I mentioned when I made my little pitch. It's essentially the standards need to hone in on something really nice. One parallel, one serial would be really great to enable a chiplet industry to follow it. So I can go to multi-vendors and I can have multi-sources. That being said, I don't know if the industry is going to go in that direction. But essentially, it's going to be driven a lot by your PPA requirements. Whether you want a paddle or a serial interface is what first decides how much your bandwidth needs to be, what kind of data you're trying to get across, the distance you're trying to drive, because the reach is different for each of these. So it's not an easy one to pick and to have a standard across the industry. But really, I think it would be driven by PPA at some point if there are way too many standards that everyone's trying to push.
Okay, great. I'm going to try and get in one last question. I've been told we got 1 minute to finish up. Do any of the panelists have experience on how to deal with RMAs and field returns for chiplets? All right. Sounds like it's a new novel area that we're going to have to figure out as an industry how to handle this. With that, I'm wrapping things up. Fantastic job by the panelists. I appreciate your support on this, and thanks for the feedback and the input.
Thank you.
Thank you, David.
Thank you, David. Thanks, everyone. This is a great discussion. So now we are at the end of the workshop. So before we disperse, Michael, if you can please share the poll, and then DJ will do the wrap up. I think we can move on to the next one. Thank you, everyone, for your feedback. Now DJ will do the wrap up.
Yeah, so I'm going to try to share the screen, or Ravi, do you want to share the screen and we can run through the slides? That might be faster. I'm trying to share my screen, but
DJ, I am sharing my screen. Can you see my screen?
no, I cannot see your screen.
Actually,
DJ, we're actually seeing yours right now. And now no one. Ravi, I'll go ahead and hand that back to you.
Okay.
Perfect.
Do you see the thank you screen, or which screen do you see?
We see the agenda screen, Ravi.
Oh. How about now?
Again, the agenda screen.
Do you see now the?
Yes. Yes.
Sorry about that.
No, no
Okay.
problem. I think we can go in the presentation mode if you can.
And then just swap your display settings, Bobby. Thank you.
Perfect. So we had over 3 hours of amazing content, and thank you everyone, especially the audience which stayed through the content. The workshop cannot be successful without active participation from the audience, and all of you were amazing. Thank you all of the panelists, all of the speakers. You all put in a lot of time and effort into your content and sharing your thought process with everyone. Much appreciated. And last but not least, thank you for the OCP Foundation for doing an amazing job of organizing this. It truly takes a village. So there are a lot of people who came and participated and contributed to this workshop. Thank you, everyone. Next slide, please. So as we heard, Chiplet business opportunity is massive. There has been a business market study by IHS Markit, and truly the opportunity is here and now. Our goal is basically to try to solve for gaps on the business side. We all can solve things on the technical side. We have absolute confidence on that. Business is a little bit more tricky because it can be ambiguous, and hopefully this workshop is one of many workshops which we are going to have so that we can solve the gaps and you can leverage what you learn to develop your business. We want each and every one of you to be successful in running businesses and bringing chiplets to market. And that's our goal here in building this open ecosystem. Next slide, please. We went through the entire gamut of the value chain. We went from design to build to deliver to talking about end user experiences. At the end of the day, what we want to basically achieve is continue this conversation, right? You want to bring this thought process again and again in different nuances so that people can continue to inform themselves and learn. Next click, please. And the idea is, chiplet use cases are evolving. We are discovering new things pretty much on a monthly basis, or and that's why this constant conversation is important. This is not one time and done. This is start of the journey, and we need to have more of these conversations. Next slide, please.
Transition.
We absolutely need feedback from all of you to make ourselves better. So please, please, please share your thoughts, your inputs to either Bapi or Michael. We would really appreciate and love to hear from all of you to see what did we miss in this workshop? How can we be better? What areas do we need to cover to help you and your business? So use this as an opportunity to be a little bit, thinking from your own perspective and see how you can benefit, your business, your company can benefit by leveraging ODSA. This is a community for everyone, and you have as much right to derive from this community as you give. So please provide us feedback on what we can do to deliver better information to run your business. Next slide, please. And that's it. We are on a long journey, and hence we have to do it together. If it was a sprint, we could run fast by ourselves, but every one of us has thoughts on whether it's going to take 2023 or 24 or 25 for these chiplets to arrive. So it's a long haul, and let's do it together. So with that, we are wrapping up on time. Thank you again for spending your Friday morning with all of us. I wish you a wonderful rest of the Friday and awesome weekend. Bye.
Bye. Thanks, everyone.
Thank you.
Thank you.
Thank you.
Thanks.
Thanks all.
Thank you.
Thanks, guys.